I think we're about ready. Everyone hear me okay? The mic is on. Is it? So hello and welcome to the seminar room here at the National Maritime Museum, and welcome also to Ice Worlds. So for those of you who haven't been here Thursday and Friday, it's a 3-day festival that's all about polar science, old and new technologies, and of course a chance to see the majestic RRS, Sir David Attenborough research vessel that's currently moored near Cutty Sark. And you'll get a chance to see it before it sets its very first mission, traveling all the way down to Antarctica. So if you haven't seen it already, do grab that opportunity. There's lots to take in today. There's exhibits, talks, tours, storytelling, and there's also a penguin parade at 4 p.m. late today. So if you're around, do take part. I think that'll be a lot of fun. But for now, we've got our 11 a.m. morning talk with the title Citizen Science, Counting Walrus from Space. We will learn about the Citizen Science project that is using satellites to count the walrus population. We'll understand how the climate crisis is affecting them, and we will also find out how we can become walrus detectives. So we've got with us Hannah Cuben and Rod Downey. So Hannah is a researcher with the British Antarctic Survey who focuses on developing the use of space technology to study marine wildlife in remote places. And we've got Rod, who has been working in the polar regions for 2 decades, initially at the British Antarctic Survey, and for the last 6 years with WWF, or the World Wildlife Foundation. And I think with that, it's over to Hannah and Rod.
Thank you very much. Thank you very much, Hans. You may be able to tell that I have been talking a lot for the last 2 days, and I'm losing my voice. So I'm hoping that I'll be able to get through the next 10 or 15 minutes before I hand over to Hannah. So excuse me for that. There we go. Great. So so my name's Rod Downey, and I lead the polar program for WWF, based here in the UK. And I'm joined by Hannah, who is one of the world's experts in using remote sensing to count wildlife. So really honored to be sharing a stage with you, Hannah, this morning. And yeah, we're going to talk to you about this really cool, new, exciting project. It's a 5-year project, and it's called Walrus from Space. And our aim is to better understand walrus populations, how they're responding to the climate crisis now, and how they might respond in a climate-altered future. And we're doing that in order to provide evidence to support the conservation and management of the species. There we go. But before we go into that, and for those of you that might not know the walrus, well, let's start by introducing you. So they're a key species in the Arctic marine ecosystem, and they're also of immense cultural importance and significance to Arctic people. And they're easily recognized by their sheer size. You know, some of these big guys can weigh like 1.5 tons. I mean, they're huge. And of course, they're recognizable by their magnificent tusks, which are surrounded by this mat of bristles. And it's perhaps the tusks that are their most remarkable feature. They're actually enlarged upper canine teeth. So they don't use them for feeding. They use them for a number of things. They use them for keeping breathing holes open in the ice. They use them for fighting and for displaying during the mating season. And they also they use them for literally hauling themselves out of the water up onto the sea ice. Okay, thank you. And that's where they're usually observed, is out on the sea ice, on these floating ice floes. They rarely move far from the coast or from the shallow waters of the continental shelf, because that's where they feed. And they're very good divers. They can dive to 100 meters or more, but generally they'll do fairly short, shallow dives to around 10 to 20 meters to the seabed, to feed on the sorts of food that they eat, like mollusks, so things like mussels and sea snails, and they can eat more than 1,000 mussels in one single meal. They've got voracious appetites. And some of the big guys, some of the really big walrus will even feed on other marine mammals, so smaller species of seals, for example. There we go. So they're only found in the Arctic. Well, I say they're only found in the Arctic, but of course, we had Wally, who graced our shores this year, Wally the walrus, who was a young adolescent vagrant. But generally, they're only found in the Arctic. And this map shows the distribution of the walrus. This was one of the first outputs from our project. And it shows that walrus have a discontinuous circumpolar distribution. So at the top of the map, there are two recognized subspecies of walrus. So at the top of the map, you can see the Pacific walrus. So the Pacific walrus are found around the Bering Sea, the Beaufort Sea, and the Chukchi Sea. And then at the bottom of the map, that's the Atlantic walrus. And they stretch from eastern Canada across to Greenland, up into the Norwegian Arctic around Svalbard, and into the Russian Arctic around the Kara Sea. And then you have this third subspecies called the Laptev walrus, although it's generally thought that the Laptev walrus are actually the westernmost extent of the Pacific walrus. But the scope of our project is solely to focus on the Atlantic walrus and the Laptev walrus. And this is the problem that we're facing. So Arctic people and Arctic nature are facing the reality of the climate crisis. The Arctic is one of the fastest warming places in the world. It's warming about 3 times faster than the global average. Sea surface temperature is increasing very rapidly, and that means that sea ice, and sea ice is frozen ocean, is in decline. And this decline in sea ice is really one of the most visible signs of the climate crisis on our planet. It's happening throughout the year, it's declining throughout the year. It's declining in all seasons, but it's particularly declining during the summer months. And we're losing about 13% of sea ice per decade. And so it's predicted that the Arctic could be virtually free of sea ice during the summer months within our lifetimes. And that has huge implications, both for Arctic species and for Arctic people. But those implications actually go beyond the Arctic, because sea ice effectively acts like a global thermostat. It helps to regulate the temperature of our planet because it reflects the sun's energy back out to space. But with the decline of sea ice, so we're effectively removing that bright, white, reflective surface and replacing it with a dark blue ocean. And of course, dark colors absorb heat. So that's further increasing the temperature of our planet. So let's come back to our walrus. Now, we saw earlier on that they're really big, powerful animals, but they're also incredibly vulnerable to the climate crisis. And the reason why they're vulnerable is because they spend so much of their life on sea ice, as you can see here. They use it as a platform to give birth and to nurture their young. They use it as a platform to haul out on when they're feeding. But as that sea ice is diminishing, what we're noticing is that in parts of the Arctic, the walrus are increasingly hauling out in greater numbers and more often on land, on the beaches. Now, walrus are really sociable animals. They're very social animals. They're used to being in large groups, whether they're at sea or on the ice or indeed on land. But as these beaches become more and more overcrowded, well, that can have really catastrophic effects, because if the walrus get scared, if they get spooked, whether that's by humans or by predators, such as polar bears, they can stampede, and they'll stampede towards the coast. And as they stampede, they can crush some of the young, some of the smaller walrus, and that can be fatal. Also, because they're spending longer on land, that means they have to travel further and therefore expend more energy in order to feed, especially as their local supply of food becomes depleted. And so that increased energy expenditure can also have an effect on breeding performance. Also, we're seeing that the Arctic Ocean is becoming more acidic as it's absorbing more of the carbon dioxide that we're emitting. And that has really serious implications for the shell-building animals, so the mussels and clams and the sea snails that walrus feed on. And then layered on top of all of that, because we're losing sea ice, the Arctic is becoming more accessible to development. And so development activities such as shipping and aviation and industrial development can also further disturb the walrus. So that's the problem that we're facing. Now, it's clear that in order to help to secure a future for walrus in the wild, we need to better understand them. But that's a really, really difficult thing to do because, of course, the Arctic is vast. There are parts of the Arctic that are remote. It's a very difficult place for scientists to work. And as we've seen, walrus can be very easily disturbed by people. So that's why we've teamed up with a company, a satellite imagery provider company called Maxar, and with other partners right around the Arctic. And we're asking for the public's support. So we need about 500,000 walrus people to help us count walrus, or walrus detectives. And you can do that on the new citizen science platform that we've launched. You don't have to go up to the Arctic to do that. And I'm going to hand over at this point, as my voice is just about to go, to Hannah, who'll tell you exactly how we're going to go about doing that.
Thank you, Rod. Hi, everyone. So yeah, now to try and count walrus across the Arctic, we've collected loads and loads of satellite images, and now this is what I'm going to show you. Oh no, I'm going to click this way. So this is a lot of text. You don't have to read it. I'm going to take you through each of them with like nice images, so it's a lot more understandable. But these are the 6 big steps we have to go through to reach our aim to better understand walrus so we can safeguard their future. So first things first, we have to know where they go. So with this project, we're focusing on the Atlantic and the laptail walrus, like Rod showed you earlier. And all the brown dots you get to see here are where indigenous people, local communities, and scientists have told us walrus come and haul out in these places, and they tend to come back there every summer. So that's what we targeted with satellite images, because we knew walrus should be there. So now we knew where they are, we needed to know when. So during the summer in Svalbard, over here, and then Franz Josef Land, we know they like to be here during July and August. Then Canada and West Greenland, it'll be more like later down the summer, late August, September. So we try to get images when we know they'd be there. So once we had that information, we gave all this to Maxar, and we were like, please, can you collect loads of images for those places? Because those commercial satellites we're using are only going to get images when you ask them to, compared to other like NASA or European Space Agency satellite that just continuously get images. But those NASA and European Space Agency satellites, the resolution is not good enough to spot the walrus. So we thought, let's use Maxar. And first year, really pleased, we were able to cover and get good images for 86% of all these places. So those are all the red dots you get to see. Then for all the crosses, those images were just covered in clouds, or they were just too dark. So even if they were walrus, we would never see them. So bad timing. So we tried then in 2021 to get more images. And here we succeeded. So last summer, we were able to get a lot more images, 96.6%. So now we have a lot of images of walruses. I'm sure a lot of you would like to know what walrus looks like from space. And actually, I mean, I'm going to show you now, but if you want to see more of those images, we have a stand, Walrus from Space, where you can actually see how the citizen science work and ask us more questions. But this is a satellite image from an island in Russia. And here you get to see a group of walruses. And if we zoom in, it is incredible. You can actually see each individual walrus. And this is because of the very high resolution satellite images, because each pixel in it is going to represent 30 by 30 centimeters or 50 by 50, depending on the satellite we used. Or if you prefer feet, it's 1 foot by 1 foot. So it is incredible. We're not able to do this, but as I showed earlier, we've got a lot of those images that we need to go through. And not all of them will necessarily have walrus because they move throughout the season and during the day, but this is where you can help us be a bit faster, because and we need to understand what's happening with walrus and their population trajectory as fast as we can. And this is why we have this citizen science campaign. Walrus from Space. You can all become a walrus detective today if you want. You can come and see us at the stand and we can show you how to sign up and give you a bit of a hands-on so you get a feel for it. But we decided to, before counting, to detect all the images where walrus are. So for all the satellite images we collected, we cut them in little chunks of 200 by 200 meters. And then randomly you're being fed one of those images and you can say, yes, I see a walrus, or sorry, there's none in that one. Or sometimes the image is a bit poor, because although we only collected the good quality images, in some of them you still had a bit of cloud or a part of the coast that was still in the shade. And this is how it looks like. You've been given an image like this one. On this one, unfortunately, there aren't any walrus. But if you come to the stand, we can show you more images of walruses from space. And then on the right side, you can see the various options you can select. So yes, walrus, no, or poor image. So once we'll have gone through this phase, we'll be going through counting walrus. And for this time, either we'll be asking the public, so any of you that would like to do it, to put a point on all the walrus you think you see. For those holdouts, it's quite easy because the walrus, like, although they're really close together, they're quite spread out as well. So you can see it in all of them. But if I show you this image, they form a very larger and tighter group. So counting them, I dare you to try. I've tried and I keep getting different numbers. So the best way now would be to draw an outline around them. And this is what scientists already do in the Arctic. When they fly drones above their holdout, they can't count them. They've tried, so they create an outline around them. And because we know the average size of an adult, then we're able to estimate. And this is allowing us to then build those population trends over time. And one thing we need to do as well is calibrate our counts, because walrus will come on the beach, but then sometimes during the day they're going to go, and throughout the season that's going to change. So Sentinel-2 is one of the European Space Agency satellite that continuously collects images when there's no clouds. And this, although you can't count each individual walrus, the brown patches you see here are the walrus. And you can see how the patch gets bigger and move along the coast. So this can also give us an idea how the variation in numbers and sizes. And June, they were not all there. And then by October, they were all gone. So it's helping us refine the science every time. And then once we have those counts for every year, because we're going to be collecting satellite images every summer and then asking whoever from the public and around the world to help us detect and count walrus, then those counts will be looked and compared with a lot of environmental variables to understand how this is likely to impact them and how this is linked. So this is a map of sea ice in winter, and all the purple pinkish area are the continuous sea ice. And as you go on the edges, when you see, or sometimes even in the center, the more yellow and green, those are like more broken ice. So you will be linking all those counts to then the sea ice data to understand how this is impacting walrus. So then we can understand what kind of maybe solution or what is the future for them and how we can help save walrus. And as Rod showed earlier, the white line you get to see here, that's the sea ice reducing. And then the orange line, that's what has been modeled. And so we think that by 2080, based on the average of all the models that have been tried, there'll be a summer-free sea ice in the Arctic. And walrus do rely on sea ice, so this is going to have an impact, but what impact? And this is what we're going to be predicting with the counts and using the sea ice once we know better how this impact them. So thank you, everyone. Now, if you would like to become a walrus detective, we have a stand on the ground floor on the other side of Ice World. So you can sign up and we can show you a bit how it works. And you could help us feel our big vision of better understanding the future of walrus so we can ensure they have a future. And then I think now we'll have time for a few questions now. But if you have more questions, feel free to pop to the stand. Thank you.
Thank you, Hannah, and thank you, Rod. Yeah, I think we've got about 7 minutes for questions. So here's your chance to ask anything you like about what you've just heard or seen. And for me, I was struck by this is fascinating, but it's also sobering, and that there's a chance to take part effectively. I think is really special. But are there any questions, or would you prefer to ask in person at the stand afterwards, perhaps? Yeah? And if you want to raise your hand high up, and then I'll come over. Yeah? What's your question? What's it like being a scientist? Thank you.
So there are very different ways of being a scientist. I'm usually just behind a computer because I look at satellite images a lot. But then sometimes you do get to go in the field as well. So next summer, we'll hopefully be going to some of those places where walruses are so we can even better calibrate our data. So we'll have some drones and make sure we do the right count. So yeah, you're behind a computer like a little spy looking at satellite images, if this is what you will enjoy doing. Or then I have colleagues that spend hours and days in the lab and preparing their samples. Or there are very different ways of being a scientist. So if this is what you like to do, I'm sure you can find what matches you.
Thank you. Who else wants to ask a question? Here we've got one. Thank you. How do the satellites work? Good luck with that one.
Yeah, that's a tough one. I'm not an engineer, but what I know is that the satellite we use, so they're like very far in space and they're orbiting constantly around our Earth. And when we say we want an image, some engineers ask to collect it. And it's a bit like a very fancy camera because our cameras are going to take an image and that one is just going to be even more detailed. So imagine you have a camera constantly looking at the Earth.
Thank you. Who else? Yeah. Got a question over here. Thank you. What's the biggest number of walruses that have been spotted in one group?
Yeah, I think the voice is just holding out. So, excuse me.
So there can be very large groups. I think it's about 100,000. In the US, they can have like very large groups sometimes. That's more the Pacific walrus. So, yeah.
Thank you. Who else? Right.
I had a question about the data collection. So when you do the area collection, when you do the area collection, they seem to pile on each other a lot. So does that complicate the calculations, and how do you know that these estimates are true?
Yeah, a very good question, because this is one, we're trying to find out. So for when they like pile up on each other, the best way that scientists that have been studying walruses for a long time have done is drawing this outline around them. And then depending on the holdout and the location, they know whether it's mostly males or mostly females that come there. So then what they'll do, they'll use the average size of a female or a male and then time. So you get your area and then you can like extrapolate this. But then if you use the same method every time you're counting them, then you're able to see a trend. It's if you change your counting method, then it's a lot difficult, but stick to one method.
Thank you. Who else? Yeah.
I was just wondering if you could use artificial intelligence to monitor the imagery, something like Tesla would use to analyze the imagery and then do the thing that you want people to do, spot the animals.
Yeah, that's actually something we want to do. So with artificial intelligence, you first need to have one image where you know you have walrus and be sure, and you need a few of them because walrus will have different colors. So that's going to change. So that's one thing we're also doing now. Like we collecting all those training data so we can look at this. And the Sentinel-2 images, which are not as high resolution, but where you can see the patch moving, this is where we're first going to try artificial intelligence to really tell us where they are initially, and then we can get the higher resolution and count them. Thank you.
Right. We've got a question over here. Yep.
Maybe a less serious question, but when they eat 1,000 mussels, do they open them individually, or are they eating like the shell?
Right. The question is, do the walrus open the mussels, or do they eat them with their shells?
Okay, I'm going to hope I can speak this time. Yeah, so the way that walrus feed is just incredible. So they're on the sea surface, on the seabed, and what they do is they use their flippers effectively to clear the sediment away. They use their bristles around their nose, which are really sensitive, to find the clams. And then they literally suck the clams and the shells out. It's just remarkable. I'm glad my voice held out for that one.
That's extraordinary. Thank you. I think we've got time for one, maybe two more questions here. Yeah, young gentleman here at the back. Thank you. How many bristles do they have?
We're going to have to set up a new project to count walrus bristles, clearly. I honestly don't know how many bristles a walrus would have, so it's a great question. But they cover this kind of area of the face around here, so around their tusks, that area. But yeah, it's a bit like maybe like your dad's beard or something, you know.
One last question before we need to break. Who wants to ask the final question? Got another question here from a young lady. Thank you. How many walruses are there in the world?
So it's estimated to be 225,000 around the whole of the Arctic, so the world. Yeah, so yeah, 225,000.
Well, that answers that.
Yeah.
And if I understand correctly, the audience can come and find you at your stall afterwards,
That's
which is up on the
correct.
Great Map.
No,
that
it's
correct, or is it down-
downstairs. It's on the same floor,
Downstairs on the same
but
floor.
on the other side of the Great Map.
And that concludes our talk today. Can we give another round of applause for Rod and Hannah? Thank you very much. in our room here at the National Maritime Museum, and welcome to Ice World, so the last day of the 3-day festival, which is all about polar science and old and new technology, and also, of course, a chance to see the venerable and majestic RRS Sir David Attenborough, which is currently moored near Cutty-Sark. So if you haven't seen it already, then do make your way down and take a look. It's a nice sight indeed. And it's about to set off, I believe, either tonight or tomorrow, we'll find out, on its very first mission down to Antarctica. There's lots to take in still on this last day. There's exhibits, talks, tours, storytelling, and a penguin parade at 4 p.m. So do join for that if you can. But for now, we've got our noon talk with a very special guest who, for a very special reason, is joining us remotely from the RRS Sir David Attenborough. Captain Will Watley is coming to us remotely to talk all about the ship, what it's like on board, about the first mission, hopefully, and about practicalities of working and living in Antarctica and modern techniques for ice breaking and polar navigation, and what the marine team does on board the ship. So the captain of the research vessel has been working in the polar regions for the last 10 years, where he joined the British Antarctic Survey in 2008 as third officer at the age of 19. His first Antarctic season was back in 2015. And with that, Captain Will Watley, can you hear us and see us okay?
Yes, I can. Good afternoon.
Brilliant. Well, over to you.
Thank you. To begin with, I would like to apologize for not being able to be there in person. The main priority for the British Antarctic Survey in this upcoming Antarctic season is to keep the Antarctic free. And as a result, when we leave here, we are actually going off to do a hard quarantine for 2 weeks. So we're all sitting in a hotel and we'll do several PCR tests so that we can live November. That we are COVID free, and anyone else joining the vessel throughout the Antarctic season will have to go through the same process. So it's a very exciting time for us. As mentioned, the ship is here. For me personally, this is an incredibly exciting moment because I project since this was just an idea and since it was just drawings before there was anything tangible at all. And here we are now with the ship ready to deploy to the Antarctic. And it's been 5 years for me that I've been working towards this moment. Tomorrow morning, and we're going around to Harwich to load some cargo. The ship will be for the Antarctic, and we have 2 crews. And we do so the crew change. So the other crew.
I'm really sorry to interrupt, Captain Watley. I'm very sorry. Can you hear me?
Finally,
I'm really sorry to interrupt you, but the connection our end is not very good.
Yes,
is it possible to maybe try switching off your camera for a bit so we can hear you, and then we can see if it improves, and we can switch the camera on later on?
Sure. Stand by.
Thank you.
Okay. Is that better?
I think so. Let's try that.
And can you still hear me okay?
Yes.
Okay. So yes, when we leave Portsmouth in the middle of November, we will be heading straight down the Atlantic to the Falkland Islands. That will take about 3 weeks. And from that point on, we have got a jam-packed Antarctic season ahead of us. So from the Falkland Islands, we'll we will be heading down to Rothera, which is our largest Antarctic research station on the Antarctic Peninsula. And because this ship is much larger than our previous ships, we will be going alongside our new wharf that's been built there, especially for this ship. So we're looking forward to trying that out for the first time. The ship will also be visiting South Georgia, going to King Edward Point and Bird Island, as well as Signey Island in the South Orkneys. But the most important thing we're doing in this Antarctic season is the ship is going to part of the Antarctic called the English Coast, which is south of Rothera, at the very southern end of the Antarctic Peninsula, and will be inputting a lot of science cargo and fuel to support a massive collaborative science project on the Thwaites Glacier. And that is an enormous project with many different parties involved. And this ship will be delivering everything they need to continue with that. So that's really important. The ship will be coming back to the UK in May of next year, and we'll then be trialing all our scientific equipment and doing lots of maintenance so that we're ready to deploy to the Antarctic once again in November of 2022. Typically, the ship will do Arctic science in the northern summer and then do Antarctic logistics and science in the southern summer. So she's going to be a very busy ship, and she's got a huge amount of capability, which we can't wait to put to good use in the polar regions. The photo that's on the screen is from our initial sea trials when we first took the ship to sea as a Bass ship. That was in March of this year, and that's passing Tobermory on the Isle of Mull, up in the Western Isles of Scotland. And it was a beautiful day. We wanted to go somewhere quite stunning for our first trip, and that didn't disappoint. You can see from that picture there's a massive crane on the back of the ship. So that's a 50-ton crane. It lifts any equipment up to 50 ton. So the ship, as well as being a really capable science platform, has big logistics capability as well. So we can take much bigger equipment into the Antarctic. We have scientific winches on board, which can deploy equipment down to about 7,000 meters of depth. And they can be deployed over the stern, over the side, or even down through the moon pool. And the moon pool is a 4 meter by 4 meter square shaft that goes through the middle of the ship. So that when there's ice all the way around the ship, we can still have access to the sea to deploy scientific equipment. We've got a helideck now as well, which we never had before. So we can do airborne science in the polar regions too. The ship's designed to take 60 scientists and 30 crews, up to 90 people, to sea for about 60 days. So the accommodation's pretty comfortable. Just click to the next slide. So the two boats that we have on board are Erebus and Terra. The first picture up is Erebus, and she is one of our small boats which we can use for science work in shallow water. So there is a shallow water SWOT bathymetry system, which means we can do seabed mapping and science in shallow water that the ship can't get to. And there is an A-frame on the stern with 500 meters of rope, so we can deploy scientific equipment from Erebus as well. We are very pleased that the ship is called Sir David Attenborough, and it's a great honour to have the ship named after him. But we felt we wanted to retain some polar history with the names of our boats. So Erebus and Terra, as I'm sure you're all aware, were the names of the ships on the Franklin expedition, but they were also the names of the two launches on board Bransfield, which was our one of the previous British Antarctic Survey ships. After we chose the names, coincidentally, we found out that our Erebus was built in exactly the same yard as the original HMS Erebus from the Franklin expedition, and that was down in Pembroke Dock in Wales. And Terra, which we could skip to the next slide, was built in Exeter in Devon, which is just down the road from Topsham, where the original Terra was built. So it was quite a coincidence that we managed to name the boats for the right geographical locations. Terra is a landing craft which can take lots of cargo in and out of all the small bases where the ship can't get alongside. So she can either go to a jetty, like at Sydney and Bird Island, where we go quite frequently and we can discharge cargo, or she can do a beach landing and you can drive vehicles off through the bow door. And she can do around 12 knots. So she's a really handy boat. And the next slide, please. So as I mentioned, the ship is really comfortable. We do 100% crew change. So we normally do about 3 months on, 3 months off. But for half the year, the ship is our home. And we have a great team on board. We all get on very well. And it's like coming back to a family when you come back to work. So this is a picture of the bar. And then if we go to the next slide, there's a picture of the day room. So there's plenty of recreational space on board. Because also when we're doing a big science cruise with lots of people on board, we could have 60 scientists. But because there's so much different capability with the ship and the ship can go to sea for so long, we'll take scientists from lots of different disciplines and they might go to sea for 60 days. But their bit of science might only be for 10 days or a week. But the rest of the time, they're on the ship waiting to do their bit of science. And they use that time for work. So they have offices, but also need space to be able to carry on with other work whilst other scientists are doing what they need to do, which is one of the reasons we have large recreational spaces and big offices on board the ship. The next slide, please. We all eat together and the catering team keep us really, really well fed. This is the mess room and we all just go up and help ourselves to food. There is an awful lot of food on board because we can take 90 people to sea for up to 60 days and we have to allow plenty of contingency in case we get stuck in the ice over winter. We have enough so that we could survive. But also we have emergency food and rations and tents so that if we had to abandon ship for any reason onto ice or onto land, we could set up a camp and keep 90 people alive for up to 20 days. So that's a fair amount of kit. We have a whole room on the ship that is dedicated to all that equipment to make sure it's all ready to go. And the next one, please. The galley is really well equipped with lots of good equipment. We have 2 cooks and a cook steward, and it's plenty big enough for 3 people to be working. And the next slide, please. So my absolute favorite part of the job is driving the ship through ice. This ship hasn't been to the Antarctic yet, so we are really looking forward to taking her into the ice for the first time. She's got plenty of power and she's really maneuverable. We've got thrusters, which we don't use in the ice so much, but they can be used to turn the ship around in tight spaces if we need to. And we've got 2 propellers and 2 rudders. So when we need to go astern in the ice and go backwards, we can have good steerage. Where I'm sitting at the moment is in the crow's nest on the ship, and if the video was working, I could show you. The reason I came up here today was to get some good phone signal to be able to do this presentation. But this is a space that would actually be used quite a lot when we're in the ice, so that we can see further ahead and plan a route that makes best use of the leads within the pack ice. And leads are areas of open water within ice. When you're navigating in ice, you're looking to find the easiest route through, but you're continually changing your mind. And quite often you come to a bit where you would hit the ice with the ship and you just come to a stop and can't make any progress, and you have to go backwards and try hitting it again. And we call this backing and ramming. We do have to do that quite a lot. You can go backwards and try again and get a run up. What's on the screen now is actually a video. You could try clicking on it and seeing if it'll work. If not, I can try sharing screen again and seeing if it'll play.
Yeah, I'm afraid, Captain Watley, we're unable to do that, our end.
Okay, never mind. In which case, we'll skip the video, but it's a video of the ship going through the ice. maybe I'll have another go when we're doing questions at the end and see if it'll work. But the next slide is about using radar in ice. So when we're going through pack ice, it's really well, it's really good fun when you can make progress and it's good weather and we can see where we're going. That's relatively straightforward. When it gets dark or foggy or at all tricky, that is what makes it quite difficult. The ship is designed to go through sea ice, and that is salt water that is frozen. So it's just the sea that's frozen, and it's less dense than freshwater ice. So it's a lot softer. Freshwater ice is from glaciers, which then break off to icebergs, and then smaller, you get bergy bits and then growlers. So the bergy bits and growlers are the smaller bits that fall off an iceberg. And that is what we really have to watch out for, because those are the bits which can really damage the ship. When it's foggy, it's quite difficult sometimes to differentiate between the two. But an iceberg, a bergy bit, or a growler is normally higher than sea ice. So you get these shadows on the radar. So you can see that image there is from one of our previous ships. And all the yellow targets is sea ice. But you can see there are some shadows on the screen, and that is formed by an iceberg or a bergy bit where you've got slightly higher elevation, and then the radar can't see through it to see behind. And that's the bits you really have to watch out for. Sometimes when it's really foggy or dark, we tend to just stop and wait for better conditions. Patience is really key when in the ice. It can be really difficult to make progress sometimes. And rather than wasting fuel and energy trying to make progress to get to where you need to go, it can be better to just sit and wait for the wind to change. Because normally, if we're struggling to make progress, it's because there's actual pressure between the ice flows. And that pressure is caused when a lot of pack ice is pushed against a solid surface that won't move, like an ice shelf or a grounded iceberg or even land. And that pressure is what makes it difficult for a ship to make progress, because we can always break ice and move it out of the way if it's got somewhere to go. But when there's huge pressure between the flows, that's when we can really struggle. So that's the time that we tend to just sit and wait for conditions to improve, because we can't make progress. Can we go to the next slide, please? So one of the really good things about being captain of a ship in the Antarctic is we can make our own port when we arrive somewhere. So this picture is of the Ronny ice shelf, which is at the bottom of the Weddell Sea in Antarctica. And we went there with one of our previous ships to be able to deploy a lot of scientific equipment onto the Ronny ice shelf for a big science project. And when we arrived, we knew where we wanted to go. We knew we wanted to be able to moor the ship in this particular position. But there was this bit of ice in the way, and we wanted to be able to get it out of the way so that we could get the ship into there. And we couldn't get the ship in to get it out. So you can see we're there with a drill, trying to attach a rope to that bit of ice to pull it out of the way. And then we can groom an edge of the ice so that we can then drill moorings into the ice and tie up, and then we call that an ice port. So if we go to the next slide, you'll see us towing it out of the way. And then once we got it out of the way, we got rid of the bit of rope, and then we can groom an edge and go in and put our mooring ropes out. And we stayed there for about a week and discharged all of our cargo. This was with one of our previous ships, but today with Attenborough, once we get down there, we'll be doing very similar things to this, particularly this coming season as well. And the next one, please. So this is the final slide. This was taken towards the end of our first round of sea trials earlier in the year, off the Giant's Causeway in Northern Ireland. The ship has been through a very extensive process of sea trials, as you can imagine. getting a ship ready to deploy to the harshest environment on Earth is quite a challenging task. And we're doing all our final checks still now, making sure we haven't forgotten any spare parts or anything we need. But it's been a very thorough process. And I'll finish by saying that I'm really, really looking forward to taking this ship to the Antarctic. And I am happy to take any questions.
Thank you very much, Captain Watley. That was truly fascinating. We have, I think, about 10 minutes for Q&A. So if you want to raise your hand up high, then I can go around and relay the question via the microphone. Who wants to go first? Maybe I'll go first. How long will it take you to get to the Southern Ocean and eventually Antarctica?
So it will take about a week it will take 3 weeks to get to the Falkland Islands from the UK, and then about another 4 or 5 days to get down to the Antarctic Peninsula.
Right.
So we'll be arriving in the Antarctic just before Christmas.
Right, thank you. Okay, we've got our first question here.
You said that it had enough food, but do you have to refuel on the way down before you go to Antarctica?
Thank you. So there's enough food. What about refueling? Is that how's that handled?
So we normally refuel in the Falkland Islands. So we'll be stopping there, and a tanker will come alongside whilst we are at anchor near Stanley in the Falkland Islands and refuel us.
There's another question here from a gentleman at the back. Right. Comparing ships, the James Clark Ross versus, let's say, the Sir David Attenborough, how do they compare in terms of capabilities and capacity?
I think the biggest difference to start with is size. The ship is about 30 meters longer and it's much wider, and it has huge capacity in everything. So the capability, we can take more scientists to sea for a longer period of time with this ship. We've got the heli deck, we've got other capabilities like the moon pool, and the ship has got more thrusters and more power, so that in really rough weather, we can stay on station for science using dynamic positioning at greater weather limits than we used to be able to. So that will mean we'll be able to do more science and have less weather downtime. So yeah, in summary, this ship is just packed full of really exciting features, and she's so versatile because there's so many different capabilities within one hull.
And 2 helipads, was that correct?
No, just one heli deck, but we have a heli hangar that can take 2 helicopters.
Right. So I've got a question here from a young lady. Right. So a pertinent question here about reducing carbon emissions, I suppose, in terms of operation of the ship. How's that handled? So
the ship is a bit like a hybrid, like a car. So we have big battery banks, as well as having diesel engines. We burn really clean diesel, and we spend lots of time going into looking at efficiencies about how we can burn less diesel to be able to achieve the same thing. And interestingly, we're working on a project at the moment for a digital twin of the Sir David Attenborough, so that this can all be analysed real time ashore whilst we're at sea, and to see if there are any other efficiencies that can be made. But throughout the build, the ship has complied and been designed to be as economical and efficient as possible.
Another question here from a young lady. So if I understand correctly, there's talk of a system, if you're stuck in ice, to wobble the ship in order to get unstuck. Is that something that might happen? How might that work? Was that about right?
Yeah, that's what we heard in the previous lecture.
In a previous...
There is a system like that. Has the captain used that before? Is he looking forward to using
Yeah. So have you tested this, and are you looking forward to trying this for the first time?
Yes, we have tested it. We call it the duck walk feature because it can make the ship waddle like a duck. And ice, there's two ways of getting stuck in ice. It can either just start closing up around you and increase pressure, or if you drive into it too fast and then you haven't got the same momentum to get out going astern, it can nip you tight. And that's when you want to try and lift the ship to break the friction. And we have big anti-roll tanks with pressurized air ducts that can actually work as rolling tanks to start rolling the ship to get us free from the ice. The other thing we can do is we can use the crane to swing that about quickly to try and break the friction with the ice as well. So yes, I'm very much looking forward to trying it.
It sounds incredible. Visually, it conjures up vivid imagery, I think, at least for me here. A question from a young lady at the front.
Is there anything that people are usually surprised about going to the poles on the ship versus like sailing in other oceans?
So going to either the Arctic or Antarctic, is there anything that sort of catches people off guard or really surprises them the first time, I guess, that they are there?
I would just say the beauty and scenery of it surprises me every time. Even after going, I've gone most years since 2008, and it never gets old. Every time you go, you're still amazed by it, and I can't wait to see this ship in that remarkable environment.
And we will follow on Vessel Tracker. So, a question here from a nice question here. Are there any traditions that you might follow in terms of when you cross the equator on board the vessel?
Yes, there are. We will do our crossing the line ceremony, where we welcome King Neptune and Queen Nefertiti on board, and they have to grant the rite of passage for anyone that hasn't crossed before. And we read charges, and those who haven't crossed before have to go through a series of punishments, and then they get issued with a certificate. And we have asked Sir David Attenborough himself to record the announcement to welcome King Neptune on board, which we will play for the first time when we, well, the first time in anger, when we cross the equator towards the end of November.
Any other questions? We've got time for a couple more. Here's one from a gentleman at the front. Yeah, good question. What time tomorrow is the ship going to sea setting off?
8 o'clock in the morning.
8 o'clock in the morning. Okay. Should we do one, possibly two more questions? Anything else? A tough one for the captain, maybe? Go, gentleman at the front. A question about financing the ship and the operation of the ship. How does that? Who finances the ship?
So it's government funding. Scientists can apply for grants to have time on the ship for specific science projects.
Thank you. And one last question from a young man here at the back.
What's the expected lifespan of the ship?
Nice one, a tough one. What's the expected lifespan of the ship?
It's all been designed around 30 years. So we'll have to see where regulations and the Antarctic is in 30 years' time. But I'm sure the ship will still be going and still doing good polar research at that time.
Brilliant. Well, with that, I think we might actually. Do we have time for one more? Maybe is there a burning question that we can take, or should we call it a natural? Oh, there's a question here from a lady at the back. I think that'll mark the conclusion. Thank you. So is there a set number of missions and destinations in the Antarctic that you are hoping to go to?
For this coming season, we have an itinerary that that is full for the whole time. But there's probably about 15 or 20 different port calls to different Antarctic research stations for different things. And the following season will be more around scientific cruises and marine science.
Right. Well, Captain Will Watley, thank you so much. I think from our end, I can tell you can probably see from the live feed, but the audience here is just, while you've spoken, just sat absolutely transfixed. And I think possibly that we couldn't see you. Maybe the imagery that we sort of conjured might have been even more vivid as a result. Can I ask that the audience turns around towards the camera and waves and perhaps gives the captain a good luck? And a round of applause, please. Thank you.
Thank you very much indeed.
Thanks for coming.
Thanks. Bye.
Thanks a lot. See you later. Okay, I think we're about ready to begin. Whoa, that's nice and loud. Welcome. We're competing with Boatemic Boatface in the lecture theater. So some stiff competition there. But welcome to the seminar room, and welcome to the National Maritime Museum, and welcome to Ice World's Festival. This is the last day of experiencing and immersing yourself in polar science, all the new technologies, and also seeing the majestic RRS Sir David Attenborough ship. How many have seen it moored near the Katisak yet? If you haven't, you should take a look at it. It's off tomorrow on its very first mission, 8 a.m. on its way to Antarctica. There's lots to take in still today. There's exhibits, talks, such as this one, tours, storytelling, and a penguin parade at 4 p.m. But for now, we've got our 1 p.m. talk. Why past climates are key to future offshore wind farms, where we will discover how the legacy of our last ice age is providing the crucial foundations for one of our modern-day climate change solutions. So we are joined via live link. Gareth, can you hear and see us?
Yes, perfectly. Yes. Hello, everyone.
Brilliant. So Gareth Carter is a senior, I've got to get this right, a lot of technical terms coming up. Gareth is a senior marine geoscientist at the British Geological Survey with a background in geological hazards and engineering geology. Key areas of work include undertaking marine geohazard assessments in relation to offshore infrastructure developments for the renewable energy industry and seabed, surface, and subsurface mapping for foundation design of offshore structures. Does that make sense? Right, so hopefully some of this will be a little bit clarified during the next 30 minutes. But with that, Gareth, over to you.
Perfect, thanks so much. And thanks for giving me the opportunity to speak to you today, everyone. First of all, I'm really gutted I'm not there to see the penguin parade, if I'm honest. I didn't know that was an option, so I would have tried to come all the way down from Edinburgh if I could have done to see the penguins. That would be awesome. So yeah, I'm Gareth Carter. I'm a marine geoscientist with the British Geological Survey. As you just heard, yeah, a lot of my work from day to day is working with offshore developers who are developing wind farms, and I help them understand the ground conditions into which they are placing the foundations for their actual turbines. And what I'm going to talk to you about today is ice sheets and offshore wind farms, and those two things may seem mutually exclusive, and I can understand why they don't seem to go well in a talk together. But I'm hoping to prove to you today that there's more than just a tenuous link between these two, what would appear disparate topics. So yeah, quickly, this is just a talk outline. First of all, we'll fly over to Iceland. I'll use Iceland as our main example for modern glacial environments. Of course, it could just as easily be New Zealand or Canada or Norway. We have quite a few examples, even today, of where we can go and see glaciated landscapes. And then we'll come back home to Britain and we'll look onshore and we'll see if we can see any evidence that relates to what we've just seen in Iceland, any evidence of glaciated landscapes in the UK and Britain. And then we'll move further offshore into what is today the offshore environment. And we'll look at what lies beneath the seas, so effectively the seabed, and we'll see if we can find any evidence for ice ages and ice sheets on the seabed. And then finally, I'm going to try and prove to you that there is actually a link between a glaciated past and also offshore wind farm developments today. So yeah, without further ado, let's nip over to Iceland and have a quick look at the lovely environments over there. First of all, I'd make a request of you. If you can please, in the next few slides, try and freeze them in your mind, because as we go through this talk, it's going to be really nice to draw on these examples, and you can think back, oh yeah, that's what we saw in Iceland, and I can see how that would relate to what we're now seeing further on in the talk. So try and lodge some of these next couple of slides in your memory bank for later. So this is a lovely panorama that a colleague gave me from Iceland. And one thing to take away from this initially is just how complex the environment is there. Glaciated environments are highly complex and can leave behind some of the most varied landforms and landscapes and sedimentary sequences that you're likely to ever find in the geological record. So there are tons of features that we could look at in this image, but the ones I'd like you to focus on are actually not on the ice or beneath the ice, but they're the ones in front of the ice. So here we can see that this glacier is terminating in a lake, what's often referred to as a proglacial lake. I apologise, some of you may have studied all this stuff in high school or even university, and this might seem very basic, but these are important features for what we're going to be looking at later on. So here we have a proglacial lake where meltwater from the glacier ponds in a topographic basin in front of the ice. And this lake is dammed, you can see on the right-hand side, by a sort of brown ridge that's running across in front of the lake. And that's a moraine or a system of moraines where the ice is pushed. We'll talk a bit more about moraines in a second, but the ice is effectively pushed up some ridges in front of it. And then draining the lake, you can hopefully see running over the green outwash plain there, you can see some river systems, some sort of meandering rivers across that as well. So we'll look in more detail at meltwater channels too. So still in Iceland, here's another 3 examples, and they're all touching on the type of features that we've just looked at, but we're going to talk about them more specifically now. So the image on the left is very much what the same sort of environment as we were just looking at. So you've got the brown mounds of gravel and sediment, sands and gravels, and they've been mounded up into moraines. And you can see a very muddy looking lake there, and also being drained by some channels. And I think we should relate that image to the center one now, where you've also got some ridges running from sort of left to right across your image in the foreground here. These ridges are push moraines. So as an ice sheet advances or retreats, it will oscillate. So what that means is at times of particularly cold climate, it will move forward, it will gain mass, and it will push sediment in front of it like a bulldozer, effectively, bulldozing that sediment into a ridge along the front of the ice. But then as the climate warms a bit, the ice might retreat, and what we'll leave behind will be this ridge from the maximum extent that it got to. And then, of course, a cold snap might kick in again, and the ice might start to grow again, and it will push another moraine in front of it. And that might not reach as far as the last moraine. So what you're eventually left with as this ice continues to go backwards and forwards is this series of recessional moraines in front of the ice. And then the picture on the right, these chaps are taking a lunch break, I think, on top of a big sinuous ridge of cobbles and gravels and boulders. And this is something that's known as an esker. And eskers form actually within the ice typically, although can also be under the ice. But how we'd visualize it, I guess, is almost like a tunnel running through the ice itself, and you would have a stream or a meltwater channel running through the ice itself. But of course, that meltwater will be sediment laden, so it will be carrying a lot of cobbles and gravel and sands. And so as the ice retreats and melts, what it dumps there is the old, if you like, river bed from within the ice into this gravel ridge, and that's called an esker. And we need to bear that in mind again for when we go forward into the next few slides. So that's great. We've looked at Iceland, but what on earth's that got to do with offshore wind in Britain? Well, first of all, let's go and look onshore in Britain. And let's first of all pin down whether we can see examples of what we've just looked at in modern day Iceland to our environment in Britain and see if we can find evidence of previous ice ages. So before we look at that evidence, it might be worth rewinding 20,000 years ago to when the ice was at its maximum extent from the last glaciation, known in Britain as the Devonian glaciation. So on the map on the left, I tried to sort of recreate a little weather forecast effectively. And you can see that the ice symbol is located over the high ground. So really, you'll have ice forming in mountain ranges, and it will flow down into the lowland valleys. And in Lowland Valley in Scotland, for instance, between Edinburgh and Glasgow, the ice would have been in the region of about 1,000 meters thick. So it's really hard to get your head around that now when you look at this landscape, how different it would have been. But the other thing to touch on, I guess, is also in southeast England, we have a different weather symbol. We've just got cold conditions, basically. And that's because, as we'll see in the next few slides, that actually the ice didn't reach that far in the last glaciation. And so we just have to bear in mind that even though ice wasn't there, there would be an incredibly cold sort of tundra, like Siberian Arctic environment, where you'd have a lot of freeze thaw on the soils there. So even though it's not covered by ice, it's still fair to say that the whole of Britain would have been heavily influenced by the presence of the ice sheet. And so, yeah, just to touch on a few facts, as I said, it was about 20,000 years ago that it reached its main extent, and it would have covered all of Scotland and Northern Ireland, and much of North and West England, and majority of Wales and Republic of Ireland. So this is the sort of evidence now that we're looking at that can tell us how far the ice went, and really just conclusively say that we did have ice sheets over the UK and over Britain. So if we start with the image on the left, I hope your eyes can pick out these ridges running roughly from left to right across this valley. And there's a whole series of them. And all we have to do is rewind a few slides to those push moraines we saw in Iceland to really remember how these things form. So here we've got exactly the same thing. We've got a whole series of hummocky moraines right across this valley floor. And they've formed as the ice has oscillated. You know, it's pushed sediment in front of it, retreated, and continued that process. And we can now map these moraines onshore in Britain. This middle one is a bit more subtle to pick out because there's a river in that channel. And so you might be forgiven for thinking that this river has just carved a normal river valley here into the underlying bedrock and sediments. But actually, as geologists, we know that this river is far too small to have done this. So it's almost what we're calling a misfit in this example. For such a large valley, it couldn't have carved that. And so we actually think that this was formed by meltwater processes. So you remember those channels that were draining the proglacial lake we saw in Iceland? Well, this is another example of that here in Britain. And it's just being utilized really by, or exploited by that present day river network. But actually, that's a misfit, and this was formed through glacial meltwater. And the final one here on the right is, I hope you can get your eye in and see these ridges running roughly sort of northwest to southeast above the river system here. You can kind of pick them out with the help of the dark trees that are dotted in between these ridges. And yep, again, these are eskers that we saw, those chaps having their lunch on. So these really sinuous ridges that formed within these tunnels within the ice. And now let's jump down to, so those examples from Scotland, but now we're jumping down to Anglesey. And I have a specific request about this slide is to try and really remember these features because, a bit of a spoiler alert, but we're going to go and look offshore of Anglesey when we look at the seabed, and I'm sure that you can see what's going to happen. I'm sure you can guess that we're going to basically see these types of features all over the seabed there. And so here we've got something called a drumlin, and these can be depositional or erosional features. So they can be deposited underneath the ice where the ice has molded gravel and sands and boulders into a sort of teardrop shape. So if you get a boiled egg, for instance, and you cut it in half and you lay the cut edge on your table, the cut surface on your table, you're left with that sort of egg shape mound. And that's the type of morphology that you will see from these mounds. But they can also be erosional, as in bedrock features. So as the ice goes over bedrock, it can basically smooth and erode around more competent bits of bedrock, and they are then molded into these teardrop-shaped features. So as I say, just bear these in mind for a few slides when we dive under the water and we look at the seabed around Anglesey. And finally, for the last slide from onshore, before we do that, is just to look at the actual variability in the types of sediments and soils that are deposited by ice sheets and glaciers, because they are hugely variable. So the image on the left relates to meltwater sediments. So as we've touched on already, as the ice melts, it's very much sediment laden. And in fact, this is a quarry, a gravel quarry within an old esker. So one of those snake-like features we saw earlier. And you can see that it's formed a very coarse sediment. So really it's sands right through to gravels and cobbles and probably some boulders in there too. And that's very different from the image in the top right here, where you've got some really interesting, almost like artistic folded sediments. So underneath the ice, as the ice rides over sediments or in front of the ice where it pushes it, what it might do is it might fold and distort that sediment into really complex patterns and really distort it because, you know, classically sediment is laid down nice and horizontal like a layer cake, but you can see here that it's all messed up because of the presence of ice. And in fact, there's some large chunks of sand that have been wedged within those clays there. So it's a bit of a mess, a bit of a dog's dinner, to be honest. And the final image on the bottom right, the first thing to say about that is it's a picture from the 70s. The chap likes his flares. I don't know if you can make him out, but also he's not wearing a hard hat. And so I just have to flag up as a modern geologist that anyone in the room that might be thinking about going into geology and things, you have to always abide by PPE and wear your hard hat. And I wouldn't recommend you stand under a boulder like this at the best of times, even with a hat on anyway. But that aside, let's talk about the geology. And this is a boulder that's roughly the size of, well, it's much larger than a vehicle. It's probably the size of a small house. And it's being transported here by the ice because the ice has a capacity to move huge chunks of bedrock for tens of kilometers away from where they originally existed. Actually, this example, this specific one, is a bit different from ice transported boulders, because we think this was deposited in a massive flood burst. So basically, when that proglacial lake we were looking at before, it might build up a lot of water behind the moraine, and if the moraine catastrophically fails because of the pressure, you drain that lake all at once, which is very high energy flood effectively. And that's got the capacity and energy to move boulders the size of cars to houses. It's crazy the energy that these meltwater floods can have. Okay, so now let's do the more interesting bit, in my opinion, being a marine geologist. Let's go and look at the seas, or more specifically, the seabed around Britain. Just before we do so, let's touch on what was happening around the seabeds 20,000 years ago. So what you can see on the left here is a map of the UK and Britain and Ireland, and you can see the thick white line shows you the maximum extent of where the ice flowed to. So hopefully you can make that out. And you can see that it's covering much of present-day North Sea, the Irish Sea, down into the Celtic Sea, and around the Hebrides and Shetlands as well. But the important point about this, I think, is that remember that this is a lot of ice, and ice obviously is composed of water. And so sea levels, global sea levels 20,000 years ago would have been approximately 120, 125 meters less than they are today. So a lot of what we think of as the seabed today would have been exposed and would have had vegetation and animals and things on them. So it's a very different environment. And although, having said that, I think given that it's offshore, the most accurate way of thinking about weather forecasts would probably be more like a shipping forecast, for those of you that are familiar with Radio 4, for instance. So an example for the Dogger Bank area where they're currently building a wind farm would probably be something like that bottom point there. So you're talking about weather that's quite extreme, quite cold, very stormy weather. So not pleasant, I would venture to say. And so just before we look at the data, it's probably worth understanding what that data is. And so we're going to look at a load of what's called multi-beam bathymetry. And you can kind of think of it a bit like radar. So the equipment emits a noise, and that will go down through the water column, bounce off the seabed, and come back to our receiver. And the time it takes to do that, to bounce off the seabed and come back, we can use that to calculate the depth of the water column at that exact point. So in this example, and this is a good example because it's generally the colors that we like to use as marine geologists, you can see the red colors, or the hot colors, represent seabed that's higher up. So that's effectively with a smaller water column. So the hot red areas are nearer the sea surface, and the colder blues and greens are deeper areas where there's much larger water columns. So they're deeper below the sea surface. And so here's an example of that type of data. So we're now looking down on the seafloor. And hopefully you can make out a whole series of these ridges running from the top to the bottom of your screen here. And these are, I think we've counted over 20 here. And these are recessional moraines. And I'm sure that having looked at Iceland with those push moraines and then looking at Scottish valleys where we've got them vegetated, you can really see how these look so similar. And so these again are the same process where the ice moves forward and plows up sediment and creates these ridges, then retreats and does it again. And as it gradually steps back and retreats, it leaves these whole series of ridges. The image on the left of this one are a whole series of meltwater channels. So you remember in the outwash plain, sort of draining that proglacial lake, we saw some nice examples of those meltwater channels in Iceland. And there we have perfect examples here that have been carved down into the underlying sediment and bedrock even. The example on the right is something that I couldn't really show you in Iceland. And the reason for that is that these deep blue colours form what look like valleys, and they are indeed called tunnel valleys. And so underneath the ice, the water that's melting can sometimes be highly pressurized, and that can erode right into the bedrock itself, these really deep channels. And so as the ice is retreated and melted away, what's left here is a whole series of these really deep channels in the seabed. They can, of course, be infilled with sediment sometimes, so sometimes we don't even know they're there. But sometimes, like in these cases that we're looking at here, you can clearly see these deep blue sinuous channels incised into the seabed itself. And remember Anglesey? Well, we're going back there now, and in the image on the left, you can probably just see in the bottom right-hand corner, there's a little a few white specks, and that's basically the blank areas show you the northwest corner of Anglesey. So you can see that we're not far offshore at all. And in the zoomed in one, I hope you can see there are hundreds of these egg-shaped mounds all over the place. The important thing about this, I think, well, there's two things. Is one, these can give you a sense of ice sheet direction, so flow direction, because they're orientated along axis with the flow direction. But the second thing is, I think I told you a bit of a fib earlier when I said that they were egg-shaped, because here you can see some of them are quite clearly very spindly, very thin. And I don't know about you, but to my eye, it gives me an impression of something having traveled really fast over the seabed at this location. And that's indeed true. We think that these drumlins are actually giving us an idea of the speed of the ice, because we know that it was surging and flowing fast here. And when I say fast, to use examples again from Iceland of surging glaciers, you could be sitting at one end of a football stadium having your breakfast in the morning, and the ice might be at the other end of the football pitch. But by the time you come back for dinner to the same spot, the ice will be at your feet because it's surged 120 meters in a single day. So we're talking about really fast flowing ice here. And so finally, this is the meat of the talk, I guess, is what on earth has all of that got to do with wind farms? And I can completely forgive you for asking that question, but I'm hoping to now prove in just the next 3 or 4 slides while we wrap things up, that that's not such a wild leap to make, and that there is in fact a massive implications. This glaciated landscape has massive implications for our design of wind farms going forward. And the answer lies in the next slide, really. And so these are simple cartoons that I've drawn up of different foundation types that we have to use for wind farms or wind turbines offshore. And the one that's used predominantly, and I will focus on, is called the monopile. So that's the one on the left of this image. So 80%, I think roughly 80% of wind turbines offshore in Britain are built using that type of foundation. And so if you imagine a big steel tube that's effectively 8 to 10 meters wide in diameter, that's what that is. And it's driven into the seabed to depths of, say, 30 to 40 meters below the seabed, because the crucial thing is you need to make sure that that wind turbine stays upright and stable and fixed for the whole life cycle of the project, which is currently about 25 to 30 years for offshore wind farm development. So you need to know what is beneath the seabed for up to 30, 40, 50 meters, because you need to know what you're building your foundation in. And so that's the real headache for engineers, and that's where geologists come in. And so what I jotted down here is just a few examples of the type of questions that engineers and geologists have to ask themselves before they even put a spade, so to speak, into the ground and start to actually develop any turbines in the foundation. And so these are a few key questions. Is the geology nice and flat like a layer cake that we talked about? Or is it deformed and all folded and really chaotic, like the examples that we've seen in those folded sediments with the sand class within them? Are boulders present? So we saw that chap standing underneath a giant boulder. And because that boulder's been transported there, you might be forgiven for not actually expecting it to be there. But if you drive your monopile in, the pile might actually refuse to go any further if it encounters one of these like house-sized blocks. Or it might, if you glance the edge of a boulder, it might cause your pile to deviate and go in squint, which is useless again. Or it can damage the tip of your pile completely, and you may need to spend millions of pounds on new foundations, ship time to then go and install the foundation again. So it's a real headache. So you need to know that those types of boulders and things are present. Are there meltwater channels there? They might be filled with different sediments as we've seen. So they might be filled with sand, gravels, and boulders, but maybe the surrounding seabed is composed of clays. And so you would be about to install your foundation. You think, great, I know what it is. It's just a homogeneous clay. That's straightforward. But then what happens if half of your foundation goes into the edge of a channel that's filled with gravel and sand? And of course, they have very different physical properties, and they will affect like the bearing capacity for your foundation and how it behaves when it's in the ground. So you really need to know what type of sediments are there. And finally, are there lake sediments there that again will behave very differently? Remember that the soils that we saw that were all folded and faulted and really chaotic, they were underneath the ice, and they have been loaded by, as I said, almost like a kilometre of ice in the past. So if you think about the weight, they'll be really compact and they'll be very strong sediments. But we think about our proglacial lake, that's never actually had ice sit on top of it because it's formed at the ice margin, the ice has continued to retreat. And so all those lake sediments that have quietly developed within that lake are nowhere near as compacted. So they will be a lot softer and they will again have very different engineering properties. So it's so important to understand what, not just you're building in a glacial environment, but what part of that environment is it? Is it a moraine I'm building into? Is it a proglacial lake? Is part of my foundation going into a channel system? So it's a lot to consider. And so specifically, I'm going to just last slide or two, just talk about Dogger Bank, which is a wind farm off the east coast of Yorkshire. We've been working on it with the developers for the past decade. So it's just starting to go through the design and construction phase now. And once it's constructed, it'll be the world's largest offshore wind farm. So it's going to have huge capacity. And so when we look at the image on the left now, the colourful one, it's quite hard to get your head around this. So what I'll use is a bit of an analogy where you imagine you've got a sandwich on a plate in front of you. And then you take the top slice of bread and you just peel it off. And what you're looking at down below is just the sandwich filling. And that's kind of what we've done here. What we've done is we've mapped what's underneath the seafloor, the buried landscape, if you like. And in this image, we've peeled back the top 20, 30 meters of sediment to reveal a layer of what you would encounter. But crucially, this is still within your foundation zone, because remember, we're driving our monopiles to 30, 40 meters. So you're still going to encounter these landforms, but it's just that they're buried beneath the seabed, so you can't immediately see them. And so again, relying on the hot and cold colors here, we can see the hot colors form really arcuate ridges. And these are the ridges that we saw, the moraines, sorry, that we saw in Iceland. So the thrust pushing moraines, and they've thrust up big blocks. And again, if you're developing into that, it's going to have big implications for your foundation design. And behind them, you've got green basins, so cold colored basins. And these will have filled with either sediment or maybe ponds of water. So again, lake sediments, which would be very different. And finally, you've got some thick, chunky black arrows sort of snaking their way across that colourful map. And these are where we've mapped old channel systems. So of course, as I said already, these are going to have very different infill sediments to the surrounding ground around it. So again, developers need to be really aware that they're building into a very complex environment. And so this is the last slide, just before we go into questions and things. And what the top image is we're going to go back to our sandwich analogy now. You put your slice of bread back on, but you've got your knife and you've cut your sandwich in half. And so now you're looking at, if you looked at your sandwich, you're going to see a nice uniform bread filling bread. So it's very flat, very nice. That's ideal. As a geologist, that's what you want to see. Certainly as a wind farm developer, you do. But unfortunately, that's not the case because of the glaciated landscape in the past. So this is like a slice into the seabed, looking at the like a cake. You've cut it open, and you're looking at the top 50 meters here. And all you need to take away from this is how all the different colors in this represent different soil units with different properties, different physical properties. And you can see how varied they are. And so they're not laterally continuous or vertically stacked. They're all over the place because the ice has thrusted them into moraines, it's ridden over them. You've got lake deposits in the green there, for instance. So it's really such a complex environment. And the image on the bottom is basically what you're looking at above, but in an outcrop in Alberta in Canada. And you can see again the different colors in the sediments and the rocks where they've been folded and thrusted by ice. And you can see two gentlemen standing there, so you can kind of get a feel for the scale. So just to wrap up basically now, I would say if you were a wind farm developer, your turbines generally have a spacing of about a kilometre in between. I think you hopefully can now get a feel for how difficult it is to build in a glaciated terrain, because where you put one turbine is going to be so vastly different from where you put the next one or another one. And you're building with 50 plus turbines. Each turbine location has to be carefully studied before you think about entering a monopile into the subsurface. So it's incredibly complicated. But with that, I'd just like to say thanks so much for your time. And I hope that was interesting in some way. I try not to make it too engineering, but thanks. And yeah, happy to take any questions.
Gareth, thank you so much for that. Hugely fascinating to have an insight into your research there. Installing wind farms, I think we all could expect that it's complicated, but quite as complicated as that. And with all those implications of the state of the planet 20,000 years ago, I think that was hugely fascinating. Any questions, tough or easy, for Gareth?
Easy, please.
Was that all a bit much to take in? We've got a question here from a gentleman at the back. I'll relay the question. Who owns the seabed?
Really good question, actually. Yeah. So theoretically, well, not theoretically, it is owned by the Crown Estate. So the Crown Estate is responsible for leasing out the seabed to all these developers, and that includes even if you're doing like a subsea cable, for instance, it could be a telecommunication cable or to get the energy back from the wind farm back into the onshore national grid. You still need to have consent from the Crown Estate for that entire cable network and for all the areas that you're leasing to build your turbines themselves. So yep, the Crown Estate is the custodian. The good news for us as the general public is that profits that are made from wind farm developments actually go into the treasury. So going forward, in the past, wind farms offshore have been subsidized to try and get them off the ground. But a Carbon Trust report from 2020 last year says that if energy costs and the price of energy gets back to what it was pre-COVID, then we're expecting offshore wind farm developments to start to actually make profits and generate income. And that's all going to go into the public purse. So there's actually a real benefit for us as the general public from these things. Sorry, that's a bit of a deviation from the short answer would have been the Crown Estate. But it gave me an opportunity to also flag up that we also do benefit from this as well. It doesn't just go into the Crown Estate themselves. They put it back.
Do we have time for one more question before we break? Yep, got a question here.
In terms of the viable area for wind farms, how much could we increase the current capacity?
With regards to the viable areas, currently, how much could we increase capacity of rolling out wind farms?
Yes, I think yes. So if I understand right, we're basically talking about what areas of seabed are viable and what ones aren't. Is that basically the question? Yeah.
Yes, it is.
Yeah, that's perfect. Yeah. So traditionally, so this is a really good question actually, because there's a lot of optimism and a lot of hope behind this question and the answer. Because in the past, we've been one of the main limiting factors is water depth. Because as you can imagine, you've got to account for all the steel in the water column. You also have to account for all the wave loading and the wind loading. So your turbine's going to be vibrating. You don't want a really long one. So in the past, we've been limited by water depths to depths of say 20 meters, 30 meters. But and that obviously has implications for what areas you can and can't develop. But the key thing here that I really like about this question is that we can now look ahead to floating wind, which is actually going to start coming online. We have one wind farm with just 5 turbines offshore Scotland, but that's being developed and it's actually functioning really well. And so in the latest round of projects that have been proposed, there are a significant number that are anchored to the seabed. So if you imagine you've got like a turbine that's floating on the top and it's got several chains or mooring systems down to anchor points on the seabed. So a different type of foundation design. But that will open up water columns to basically almost make it limitless where we can do that. We won't go off the continental shelf into water depths of 1,000 meters or something, but the UK continental shelf is actually quite shallow. It's generally less than 200 meters. So I think we're going to be looking at huge expanses of these now if we want to, and there's an appetite for it. So yeah, I think the positive things is many areas.
And I think with that, we'll draw the session to a close. Can I ask that the audience turns around and looks at the camera, and we might give some applause to Gareth Carter and thank him for this fascinating talk. Thank you very much for coming.
Thanks so much, everyone. Yeah, thanks for giving me the time. Really appreciate it.
Thank you very much.
Cheers.
two. 2, 1, 2, 1, 2, 1, 2. Test, test. 1, 2, 1, 2, 1, 2. Test. 1, 2, 1, 2, 1, 2.
It's great to see that the conversation is already going. Try not to get feedback here, but thank you all so much for coming today to the seminar room here at the National Maritime Museum. I think there's some more audience coming in here. Maybe we should wait. Come on in, welcome. So, and also welcome to the Ice Worlds Festival. This is the last day of a 3-day festival, which is all about polar science, in case you hadn't guessed yet, old and new technologies, and of course also a chance to see the RRS, Sir David Attenborough research vessel, which is, well, it's right there, and currently moored near the Cutty Sark. So if you haven't already seen it, do go and take a look. It's quite a majestic sight, I think. It sets off tomorrow to Antarctica at 8 a.m., I'm told, by Captain Watley. There's still lots to take in the final few hours of the festival. There's exhibits, talks such as this, tours, storytelling, and a penguin parade at 4 p.m. So do join for that. I think that'll be fun. So I should specify, you're right, it's not real penguins as such. It's people dressed up as penguins. Yes. Good question, though. But for now, we've got our, 2 p.m. talk with the title Mission to Zero, How Will Ships Be Green in the Future? Most of the stuff we buy, I suspect most of us know this, but pretty much all things we buy, and indeed all things in this room, including the tech at the back here, arrives probably via container ships, big, fat, monstrous container ships from somewhere else in the world. And this is a trend, a global trend in trade that is expected to grow and grow during this century. So how will shipping play its role in reducing emissions in the future, and why is this important? In this talk, we're going to find out about what the future looks like, and we're going to hear about a project in London that is leading the way. And we're joined here by Neil Ryan, who works for Innovate UK, helping businesses to innovate. And we're joined by Ben Murray, who is Chief Executive of Maritime UK, which represents the UK's diverse maritime sector. And lastly, but certainly not least, we're joined by Matt Ray, who works for Arup, a global engineering and consultancy business involved in maritime innovation. And with that, over to you, gentlemen.
Thank you. And firstly, thank you for turning up. We weren't really sure how many people would want to come and hear about ships, but it's great that we've got an audience. So my name's Neil Ryan. I'm a senior program manager at Innovate UK. I'll get the slides to move on. There we go. So we're part of the family of organisations alongside British Antarctic Survey. So we invest in science, research and innovation. And as you can probably tell from our name, we're focused on the innovation part of that threesome. So we're a triple act today, along with Ben and Matt. We're going to tell you about what we're up to at the moment in terms of maritime innovation, what's going on right here, right now, including on the Thames in London, but also talk about where we want to get to as a sector going forward. So I hope you find it informative and enjoyable. So why does innovation matter? So let me start with a quote from no less than Albert Einstein, who said, "We cannot solve our problems with using the same thinking that we use to create the problems in the first place." And that's certainly true for addressing the challenge of the climate emergency. So we need to use innovation. We need to do things differently. We need to use new technologies to move from where we are today to where we want to be in the future. And that can be across all aspects of how we live. So future zero-emission aircraft, driverless cars, and certainly zero-emission cars, new forms of quantum computing and power electronics, but also energy storage and batteries. And at Innovate UK, we work on all of those technologies and much, much more. Everything from sustainable packaging, space technologies, materials, manufacturing. We're here to support innovation right across the UK. So why does it matter to maritime? So maritime is now beginning its journey to transition towards net zero. That includes everything from a technical term here, little boats, to big boats. So including the stuff that you see on the Thames, the stuff that you see around the coast of our country, including out servicing wind farms, but also the very large super ocean-going vessels as well. but it also means innovation in our ports and harbours. And the discussion we've been having down here at the front already is around, when a future ship arrives at a port, it's potentially electrified. How do you charge it? How do you literally plug it in to make sure that it's not just sat there with its marine fuel engines on, creating emissions actually while in the port? If hydrogen's a future fuel, how's that stored and bunkered at our ports? Because ports are integral parts of many of our cities. If you think about Southampton and Portsmouth and Plymouth and Aberdeen and Glasgow, the port is a core part of the fabric of the city. Right, so why does it matter to decarbonise maritime? So I've got 3 quick facts to give you. So maritime produces 5% of all of the UK's greenhouse gas emissions. So 5%, it's not massive, but that's actually more than all the buses and all the trains put together. So it's quite a share, so we can obviously reduce that. And as you heard from Hans, shipping is actually vital to how we live our lives. Something like 80% of all global goods are moved around by the ocean. And I think it's as high as 95% of all stuff that arrives in the UK arrives on a ship. But actually shipping is a very efficient way of moving stuff around. Because the vessels are so large, you can actually move a huge amount of stuff on some of the vessels. So per weight or by weight, it's actually a very efficient way of moving large quantities of goods around the world. But clearly, why does it matter? Well, the obvious reason is it matters to the planet, and it matters to addressing the challenge of climate change. It matters particularly to air quality issues within our cities, particularly people that live in those cities near to ports. But it's also crucial for jobs and growth. So, some of the most famous ships ever built have been built here in the UK. There's no reason why the UK couldn't be at the forefront of a kind of green industrial revolution around shipbuilding. And that's part of the opportunity that we have in terms of boosting innovation to create those jobs here in the UK. Okay, so the last slide for me, and aimed at the young people in the audience, and we do have at least one. Innovation can come from anywhere. It comes from big companies, it comes from small companies, it can come from literally one person in their shed with a revolutionary idea. And we're no shortage of famous innovators. I've got 2 here: Tim Berners-Lee, father of the internet, Steve Jobs from Apple. But innovators come from all walks of life. Anybody can do it. Innovation in rock and roll with Chuck Berry, a pioneer of space travel with the first female cosmonaut. So the young person's kind of wandering around at the back there, but hopefully, coming along to events like this, seeing what's going on across science, research, and innovation, we can inspire people to use their brain power, use their talents to help us on our mission. Okay, so I'll stop talking now. I'll hand over to Ben, who's going to give us an overview of the maritime sector before handing on to Matt. Okay, thank you.
Wonderful. Thanks very much, Neil. Can I just grab this? Wonderful. Well, thanks very much, everyone. I thought it would be helpful to start, just as we're in the Maritime Museum, explaining a little bit what we mean by maritime. So, first off, does anybody know where this might be? It's a bit of a sort of a geeky internal industry question, but that's Belfast. That's the port of Belfast. And you might see the Harland and Wolff crane there. So it's, recognize that? So I don't know if anybody saw that BBC drama, was it, around Belfast, and Harland and Wolff cranes were in that. But the point of this slide is to show that maritime is a sector that is across the whole of the UK. And it's something that, as you'll see, is a really big sector for the UK economy today. But just if we break it up, it means the shipping industry, so how we move, and Neil spoke about this, how we move goods, how we move people. It's the ports industry. There's a port, that's harbour, and it's clearly the ports where the ships and the vessels, and ports and harbours, sorry, where those vessels come in and they get their people and goods off them. And there's ports, I think there's about 250 ports around and harbours around the country. It's a weird one because when does a port become a harbour? But the point is, these are big hubs around the whole of the UK. And you might have seen, some of you might have heard of free ports that the government are pursuing at the moment. So these are ideas that you can unlock economic development in coastal areas through effectively making it cheaper and I think, more attractive to base a business somewhere like this. We also include the engineering and science industry. So Boating at Boatface, David Attenborough, all of that, marine science, CFAS, some of you might have heard of. It's the looking at ocean science, looking at the technology we need to assess the health of the water, all in there. And that includes naval as well. So you'll have all seen, hopefully, the Queen Elizabeth aircraft carrier built in different parts of the UK and then assembled on the Clyde. That's all maritime too. Leisure, if any of you are fortunate enough to have a super yacht or been on the water, if you do very well, you might be able to. You've got the UK's, funnily enough, home to people like Princess, Sunseeker, Pendennis, really world-leading brands, and they're all in our definition of maritime today. And then finally, professional services. So the City of London, in many ways, was built on things like shipbroking, finance, Lloyd's of London, the coffee shops, all of that. And that still, to this day, puts London as a real world leader in maritime. And the point of showing you this is that you come around a museum like this and you see the Titanic, you see, if you go down and see all the stuff in Bristol and Brunel and all that sort of stuff, maritime today is still something we do, and we do it well as a country. We can do it better, and I think the opportunity to do that is primarily in green technology and responding to climate change as a sector. So just to demonstrate that, as a sector, it might be surprising, but 1 million people's jobs are dependent. Ultimately, dependent is probably the wrong word, because as colleagues have said, 95% of trade comes in on a ship. So if that trade doesn't come in, probably more jobs are dependent. But the sort of direct number of jobs in the sector is 1 million. And it pays well. So youngsters and others, if thinking of moving around in terms of what you want to do, maritime's a sector that pays almost 10,000 more than national average. So when we're trying to inspire people to join the sector and think about the sector, it's it's an important consideration for people. I think you've heard there that maritime's worth more to the UK economy than the rail industry and the air industry. And that's a bit of a chip on our shoulder when we see government handing out loads of money to the aviation industry and to others. HS2, whatever you think of it, is a huge infrastructure investment. We could do as a sector with a proportion of that to support our future. And I'll come on to that. 95%, if you go to a maritime event, everybody stands up and the first thing they say is 95% of trade. So we're going to repeat it to all of you here because it's important that people recognize that the ocean, the sea, the people who work on ships, the people who crew them, who design them, who service them, and everything else are part of that critical lifeline support. And you probably saw during the Brexit negotiations, during COVID, you saw ferries and ships on television a lot more. And that's, that's good for us to elevate the fact that we are a maritime nation still. And I think the good news for those of us involved in the sector is it's due to double in size. Our challenge is to make sure it doubles in a sustainable way and exploitation of natural resources are done in a responsible way. So that's what it's worth. Deliberate, what is it worth there at the top? Just on, where are we here? Have I gone 2 slides? No, 1, sorry. So just in terms of decarbonisation, just interestingly, this image here is from, again, Belfast. There's America's Cup team called Artemis, some of you may have heard of. They have taken their technology and applied it in a commercial setting, and they're developing zero-emission ferries over in Belfast. It looks quite cool, but it's using the technology you can see there to lift itself out of the water as it moves, reduce friction, reduce drag. And they will have, this won't be ready next year, but the world's first electric workboat that rises in the water in this way will be available next year, which is really exciting. So just some key points on decarbonisation. Every sector is working through this challenge quite rightly at the moment, and maritime is no different. But I think, as Neil said, it's worth remembering that maritime is the most carbon efficient. It's probably quite obvious. If you think about, if you need to move something, you put it on a plane, that's going to be too heavy. It's going to take too much space in that aircraft. They might be monstrous looking ships, but they're fantastic in the way that they bring so much cargo into, well, Felixstowe when it's rolling well. If you saw the news recently about some of the HGV drivers causing delays, it just shows how critical those supply chains are. But domestic shipping emits more than buses and rail combined, which means you can't ignore it when we need to focus on net zero. And quite frankly, net zero as a concept requires everybody to go as far as they can and then use the ability to offset where needed. And maritime can go quite a long way towards being absolute zero in terms of the technologies that we think will be there. One point I think it's important to make is that unlike cars, where batteries are the option by and large, and for I see we're seeing hydrogen for buses and other vehicles, but by and large it's batteries and you plug in at a service station. For maritime, you'll have so many different solutions that are required because of the size of vessel. Smaller vessels will probably, by and large, be battery. the larger vessels, hydrogen, ammonia there as a part of the mix, and methanol as a transitionary type fuel, LNG at the moment, cleaner fuels as a transition, because a lot of people are thinking about the end goal, but not the stepping stones and the reductions that we need to see on the way. And just that last point, I think, is important, that perhaps it's Brexit, perhaps it's this focus on coastal communities and reinvigorating their economic fortunes. But the Prime Minister, for whatever reason, hopefully it's because we've convinced him and government of the need to back the sector, but you're seeing government talk much more about maritime as part of our future, and not just in a let's wave a flag and a jingoistic type way, I hope. So just quickly, I'm conscious of time, just in terms of the key elements to this, just to break it down. Colleagues here and across the sector are working on all manner of things, and perhaps they're obvious, but the most important thing to do now to make vessels cleaner and to make them use less fuel is to work on efficiency. How can you make the design such that the drag is less in the water and you need to use less fuel to push them along? There's a company called Silverstream Technologies that are blowing a carpet of bubbles around the hull to reduce friction, and that's stuff that can be done today. You can also put, this is really exciting, and it's sort of back to the future, you can put wind-assisted technology on to reduce the need for fuel. Now, the challenge, of course, is to make sure if things are time required or that just-in-time technology, that the things are still arriving when they need to. But for things that you might have a bit of leeway on, why not use wind? And that is happening and is happening at pace. Propulsion, quite obviously, how are you going to move the vessel? I touched on some of the fuels, some of the technologies that you will need to employ to move them. And the flip side of that, rather like your car, if you're going to have a battery car, you need to have somewhere to charge it. And that's the conversation we were having at the front earlier. Nobody at the moment is significantly investing in a vessel because they don't know if the ports are going to have the infrastructure. It's probably the Betamax thing is something people talk about. You don't want to invest in the wrong technology. So part of what we need to do here, and this is where the UK, I think, has an opportunity because of its role between the Far East and elsewhere, Europe in particular, in terms of cargo, container ships, is to take a lead, and then others will start to follow, because if you've got a vessel coming from China, you can't have it having different technologies along the way, because you can't have an electric car that you suddenly need to put petrol in. It doesn't work. And underpinning all of this is finance. And actually, I think there's an opportunity here for the City of London and in terms of ship finance. How can we use the expertise we have here in the city to unlock capital? Because I think some of the figures we've seen have suggested it's going to cost, I think it's around £2 trillion to convert the sector to a net zero mode of operating, which is the UK economy, the output of the UK economy each year. So it's significant. And then the last point there, the UK has been very strong in setting regulatory targets, but we need that to be matched with support, because funding, essentially, because the risk is if you just regulate, you end up in a place where we, as the UK, become a market for Japanese, Danish, Norwegian products, which is fine because it will get us as a planet to net zero, but we also want to create new jobs, well-paid jobs around the country, and you get that by developing the technologies. I'm going to wrap up because I'm conscious of time, but I think we can be optimistic about where the UK can do well. This is a hydrogen workboat that's being launched at COP. You've probably all heard of COP. We've got a hub there at City of Glasgow College for 2 weeks where we're showcasing these sorts of technologies and encouraging more people to adopt them. But because of our infrastructure in terms of offshore wind and the ambition we have there, we've got an opportunity in offshore wind in particular. And there's a few other areas, I think, where we really can lead as a country. And happy to talk about that in some of the questions that we have later on. I'm sure we can circulate these. But there are areas we can lead, and there are some exciting areas that we're already doing well and we're getting ahead. And I think we're going to hear about a couple of those now. So thanks very much.
Cool. Thanks, Ben. So Ben and Neil have very much talked about what can be done. I'm going to try and talk a little bit about one really practical application of what's going on. So there's a bit of interaction in this, so it wakes everyone up. That's why I'm on last. So my research tells me that the first settlers came to London about 6,000 years ago. Everyone here from London? London is good. So a bit of history as well here for you. And along the Thames, so we reckon they probably came here because of the river. We found sort of Bronze Age and Iron Age forts and things along the Thames. So London grew up, we all know that, because of the river. Go on, no, you go for it. So the first people we really know that used the river were the Romans. About sort of 40, 43 AD, they rowed their way up the Thames with something like this. Okay, so our first boats powered by wind, powered by oars. Great to hear some things that Ben's talked about going back to that. But in fact, the Romans even built a bridge over the Thames for them to go under. Yeah? Anyway, so pretty much not a lot changed, to be honest, until we fast forward up to about 1815, and that's when about the first paddle steamer appeared on the Thames. So down there in the bottom right, a bit of I don't know if there's an artist, or can't believe they took a photo back then, but here is when we started belching black smoke on the Thames. So we were burning coal at this stage, and then towards the end of the 1800s, well, into the 1900s, we found oil, and along came diesel. And to be honest, between the early 1800s and now, not a lot has changed on the Thames. We're still burning some sort of fossil fuel and belching it out of some sort of exhaust on the Thames. And in the last decade or so, we've realised that that probably isn't the greatest thing to do, is it? And one of the reasons we're all here today. But it's basically, as you've heard about from the others as well, it's time for the Thames to play its part in changing all this. Okay, and I think what I want to talk to you about is the biggest change that's probably going to come to the Thames in practice since the oars and the sails were put away, nearly 200 years ago. So let's sort of have a look. Let's move on one, can we? Is that right, Mr. Clicker? Right. Anyone ever used London's riverboats? God, this is good. Anyone came here on a riverboat today? Nearly? No. Oh, it's going to get you. So, but people have been on them, and it sounds like most people here have heard of them. Recently, they've been branded Uber Boat. They're actually run by a private company called Thames Clippers. And the company's actually, the chief executive of it actually was the captain of the very first boat, and he still runs it. You know him. There we go. But for those of you who don't know anything about this, Thames Clippers, now branded Uber Boat, but actually ownership and things, nothing to do with Uber. It is just a branding that they've taken on. Currently, previously, they've been MB&A, and other people have branded them in the past. But currently branded Uber Boat, and that's what we'll call them. So they're a set of high-speed catamarans that plough their way from East London. They go out as far as Hammersmith, and they go out almost to the QE2 bridge in the east. There's 21 boats, and they stop at 23 piers along the way, and a little bit of plugging. You can even use your Oyster card to go home on them if you haven't used them before. Anyway, how are they powered? How do you reckon they're powered? Spot on. So like every other bit of heavy transport, they're powered by socking-great diesel engines. Pretty much at the moment, it's the only way you can do it. There isn't anything else at the moment that will power these things. These things play along the Thames, and particularly if you see them out this far around Greenwich, they're doing up to 30 knots, these boats. They're quick. In order to sort of have some sort of competition with the tube and trains, they've got to move quickly along the Thames between the piers. Otherwise, you almost might as well walk along the Thames path. So they do that. They also have to go against the tide. And I'm sure you've played poo sticks over the bridge. You can't keep up, even if you manage to cross between the traffic. So they've got to be able to do that sort of speed against the tide, and that's not easy. So unfortunately, the one thing they do is consume vast amounts of diesel. Each one of those boats gets through about 2,300 litres of diesel a day. For those of you who've got a car, I know hopefully in London you haven't, you'd be refueling your car about 35 times a day to put that volume of fuel in. So they are thirsty beasts. And sadly, burning, keep moving on, sorry. Forgot all about the slides. There we go. So unfortunately, burning that volume of diesel, click on another one for me, produces in the region just over 6 tons of carbon dioxide a day on those boats. If you click on, and please, I've calculated these, so please don't wave them to Mr. Uber Boat. This is done off of Google by me. If you go back one. So I've calculated that's sort of over 235 trees you'd need to absorb that. So please don't quote these. This is me working it out from Google, just to give you some scale of the challenge we're trying to tackle here. So, but there's a plan to change all this. Uber Boat, Thames Clippers want to be the first to decarbonise on the Thames. So when you go out on the Thames, they're 21 boats, but there are bigger fleets out there. They are determined to be the first to decarbonise on the Thames. And actually the first to run fast river catamarans on something other than diesel. Let's go on a bit. So Go back a bit. Ruined it now. So we want to do it, and we've brought together a consortium of companies. As you might have seen, I'm not from Thames Clippers or Uberboat, but they've brought together companies, British companies, to try and achieve this. And with some help from the Department for Transport and Innovate UK, that's what we're up and running to do. So we're going to use a fuel that doesn't generate a gram of carbon dioxide. What's it going to be? You've already heard it. It's going to be hydrogen. And because it doesn't produce any carbon dioxide, I can see you clamoring to find out where you're going to get it from. Yeah? Any ideas? Any chemists amongst us? Got some chemists from? There is a never-ending source of hydrogen, it turns out. We've just missed it. For donkey's years, we've missed it. Where does it come from? It's water, basically. We've been given the most abundant substance on the earth is full of hydrogen, which is a perfect fuel. It just all became unpopular about 100 years ago in Hindenburg when there was a bit of an accident. But thankfully, 100 years on, we can work out how to control it. So water's the answer to this. Because all we need is an electrolyzer, and we can split the water into oxygen and hydrogen. Dead easy. And then we've got our hydrogen as a fuel. Let's move on. There's two ways to do it. Two ways to split. Once we've got hydrogen, there's two ways we can use it on our boats. But first of all, we get our water. If you click on, this builds itself beautifully. And we put it into an electrolyzer, okay? Basic bit of chemistry, you probably all did it at school. Stick it in, probes in the water, bits of gas. You were interested in the oxygen that came off. Turns out we're not that bothered by the oxygen. What we want is the other gas that was coming off that nobody told you about. We want the hydrogen. And if we can produce this, all we need is electricity now in our water. So we don't need the refineries of old, where we had a massive refinery at Fawley or Grangemouth, and then we had to have fleets of trucks bringing the diesel into cities. Well, if all we need is water and electricity, why can't we do it where we're going to use it? And that's what this project really is about. Hydrogen on the Thames. Hydrogen on the south side of the Thames. And it's about putting an electrolyzer that's green, so it's powered from green electricity, as close to the central London as we can to provide hydrogen for these boats. Click on. And our sort of engineers who are involved in this decided that just powering the Thames Clippers, not really enough. Because there are going to be other people wanting hydrogen. And actually, if we're going to be a zero carbon economy, what we shouldn't be doing is moving masses of stuff around unnecessarily. That's what we had to do with petrol and diesel, because we couldn't get it in London. But why don't we try and make this stuff? Let's go back to what went on 100 years ago, where we made stuff with what we had close to where we need it. So as well as that, can we use, as well as powering the Uber boats, Thames Clippers, we're also going to put in an HGV refueling station at our site, so that the HGVs of the future that are bringing goods to London have that option as well. And obviously elsewhere, there is projects going on to look at HGVs of the future. But I can hear you all crying, what about the poor oxygen? What are you going to do with the oxygen that you all loved in those experiments at school, that you collected so beautifully out your electrolyzers? You're not going to waste it, are you? Well, no, we're not. So we've realized that that has to be used as well. This isn't about wasting things. So you may know little about the sewage treatment. One of the things they do with sewage treatment is bubble huge amounts of air through to clean our wastewater. Actually, if you can use oxygen instead of air, neat oxygen, the whole plant efficiency becomes greater. It can have a greater throughput of waste. So actually, we've chosen the site for our electrolyzer to be alongside one of London's largest sewage treatment works, in the hope we can work with Thames Water, one, to pass our oxygen over and enable them to get greater capacity out of their sewage works. And don't tell them yet, but we also want some of the water that comes out of it to put into our electrolyzer to make the hydrogen. We haven't mentioned that to them yet. So sort of there we are. Very quickly, I'm conscious of time. You can just click on for me, Ben. It's very kind of you. So who's involved in this? Well, this is a British consortium. It's a consortium of UK businesses coming together to try and get this project to work. It's got massive challenges, and I'm conscious of time. I am more than happy to talk to anyone afterwards about the big challenges that this project has. But and the gentleman here knows one of them already. But here we have Thames Clippers, intricately involved. They have the boats. Shell in the top right. Shell, known to all of us for their petrol stations and their oil business, but Shell UK are also at the forefront of hydrogen creation and hydrogen refueling. So they are part of it. If you want electricity and you want it in quantity, the people to talk to are National Grid. It so happens as well that from an old oil-fired power station down the Thames, National Grid also owns some land which sits next to a substation, next to a sewage treatment works. So they are part of this as well. In the centre there is a useless building of a picture. That's where Arup are based, where I come from, who are a British firm of engineers and project managers who are working alongside this. And then absolutely last, but by no means least, up in the top corner is a company called White Boat or White Shipyard. So the Thames Clippers that you see ploughing up and down, jet propulsion boats, are built on the Isle of Wight. And they are intricately involved in this project, with obviously the hope that they will build the hydrogen-powered vessel of the future. And I think I've just about used my time, so I'm more than happy, probably outside, to have a chat about any questions.
Thank you so much. That was hugely fascinating. So Neil, Ben, and Matt, thank you. And for my mind, at least, I think for all the talks that I've heard so far, this is one of the more optimistic ones in a sense. I hope the audience has some tough, medium, and light questions for the three gentlemen. Who wants to go first?
Yeah, okay.
Start.
Sorry, if you're happy, just because...
I might do it for reasons and all that. So, yeah. Thank you. Can water to produce hydrogen?
Am I allowed to pass?
Yes.
I genuinely don't know. I'm a project manager by trade, so I'm not going to pretend to try and answer. When we've talked about using the sort of outlet water from a sewage treatment works, the engineers I'm working alongside have said that it needs minimal treatment. If we were to try and take water out of the Thames, it would need more treatment. Ultimately, the cleaner, the more pure to H2O you use, the less byproduct and things you're going to create. Obviously, if you split pure H2O water, distilled water, all you get is hydrogen and oxygen. My answer is, I think you can pretty much use anything. You've probably got to desalinate it first before, otherwise you're going to end up with the sodium chloride all over the electrolyzer. But I'm not the expert in it, I'm afraid, the engineering.
Thank you. So an additional process there to make it work, I guess. Another question here from a gentleman at the front.
Yeah, I just want to know if you're going to use a different fuel, hydrogen, in the Clippers to begin with, do you have to re-engine the boats? Can you adapt the marine diesels that currently exist, or do you have to completely repower the boats?
Great. So I'm just going to repeat that. That's a great question. What about the existing engines? Do they have to be replaced for this technology to be rolled out?
So the project is looking at two things. It's looking at the new boat, the boat of the future. Clipper Fleet are hoping to expand over the coming years. They see the river as a great way of transport. If you haven't done it, go home that way. It's fascinating. And I'm not paid by them. It is a great way to travel. And the new boats, every new boat they build now, they want to be powered by this. The project, there's a sister project to Hydrogen on the South of Thames, which is looking at boat of the future. That is looking as well at can we retrofit the existing fleet? Clipper wants to do that. The big challenge with retrofitting is the volume of, obviously the existing boats were designed for diesel. So you can't put diesel into a traditional industrial internal combustion engine. It just won't do anything. The engines are no bigger. The big problem is storing the fuel. They're designed, I'm not going to quote, I think it's about, can't remember, the volume density of hydrogen is significantly lower than diesel. So how much do you have to change the boat to get the space to put them in? At the moment, they only refuel the boats once a day down at North Greenwich. Obviously, the opportunity, there's not going to be refueling stations every couple of piers. That's part of what we're looking at is if we did a retrofit, do you need a second refueling station, down in the west? All those things are being looked at. I think that, I'm not going to try and guess the outcome of it. There'll certainly be some comms in the new year when the project comes to an end in March. Yes, the truth is, yes, they would very much like to come up with a retrofit solution as well.
Yeah, just to add to that, so you definitely can burn hydrogen in an internal combustion engine, and Mercedes-Benz are about to roll out a hydrogen truck. And obviously the engines that are used in boats aren't that different from truck engines. So that technology is not that far away. The barrier is the kind of cost implications for retrofitting vessels. And as we like to say in maritime quite a lot, our vessels last 30 or 40 years. So there's a particular challenge there because a truck will only last maybe 10, 15 years. But because our ships are in the ocean so often, or so for so long, we have to invest in a technology now, but then potentially retrofit in a few years' time, 10 years' time, for the latest technology to make the benefits from the latest tech.
The fuel storage is the challenge, to be honest, because hydrogen stored in, you've probably seen traditional cylinders. It's held under very high pressure, has to be, because unlike diesel, it's not a liquid at room temperature. So create a tank of any old shape you fancy. Traditionally, what they do is put it in the shape of the hull. Mold the tank to the shape of the hull. You can't do that with hydrogen. It's got to be those traditional cylinders to withstand the pressure.
Conscious of time, but let's squeeze in one last question if we can, and maybe the conversation can be continued outside of the session, if that's okay. Thank you. So this is all well and good for the future, but what are we doing right now in order to improve emissions?
Yeah, I'll try and take that. So this project is happening now. There are 54 other projects that we're funding at the moment that range from all types of different technology, from Shetland and Orkney right down to Plymouth. So it is underway. We are starting, but sure, there's a long way to go, and a lot of the solutions perhaps are 3 to 5, maybe even longer years away. But there is a certainly demand from the sector. There's some infrastructure challenges and some financing challenges. But certainly maritime has started, but it's got a long way to go.
I can probably add very quickly, the conversation we were having before that others weren't party to around shore power. The Thames Clipper fleet, only because I visited them as part of the project, they now have shore power for all their boats when they go back to North Greenwich at night. So in terms of, obviously, they're cleaned and refueled and everything overnight, they now plug them all in rather than leaving the engines running when the cleaners are on and things. So it's a very small step, but it's going in the right direction.
And there are electric ferries and there are hydrogen-powered vessels, so they are there. It just takes time to transition.
Idling is one of my pet peeves. Neil Ryan from Innovate UK, Ben Murray from Maritime UK, and Matt Ray from RUP, thank you very much indeed, and thank you for coming. Okay, I think with that, I've been given the go-ahead by James at the back here to begin. But yeah, welcome to the seminar room and welcome to the National Maritime Museum and also ICE Worlds Festival, a 3-day festival all about polar science. So these are the last few hours of the festival. It feels a bit sad, really, having been part of it since the beginning. But as you know, it's all about polar science. It's about old and new technologies. It's a chance to see the RRS, Sir David Attenborough ship in all its glory, moored next to the Cutty Sark. And the ship, we have been told, is setting off to Antarctica first thing tomorrow morning at 8 a.m. So do grab your chance to see the ship before it heads off on its first mission. I was about to say there's plenty to still take in today, but we're approaching the end of the day. But there is the Penguin Parade at 4 p.m. So if you, particularly the young members of our audience, if you're keen, it should be really fun. I'm looking forward to that one myself, and we'll end up near the Cutty Sark, and I think there are some badges to be handed out and so on. But for now, we've got our 3 p.m. Talk, where we will find out about living and working in Antarctica from an engineering perspective. We'll find out about working in the polar research sector and how that satisfies the desire for new experiences and technical conquest. We'll find out about the coldest places that they go and the cool things that they do and the variety of people that they work with. So I've got with me here Carson McAfee, who is an electronic engineer for the British Antarctic Survey. Over to you, Carson.
How's that? Right, well, thank you very much for coming through. I know it's late on a Saturday. So yes, as he said, my name's Carson McAfee. I've been working for the British Antarctic Survey for 6 years now, and it's been an absolute blast. So what I think we'll start with is I will just give you a quick example of a typical team that goes to Halley. So this is the team. And we'll talk through some of the people that go and the sort of the roles that are involved. So, like all things polar science related, we need a scientist. We need a scientist to come up with the ideas. We need to come up with a scientist that comes up with the questions. So, there's our scientist. So then you need a couple of engineers to look after the instrumentation that goes south. So make sure that the data that we're collecting is good. So we add 2 scientific electronic engineers and a data manager. So now we've got a small team of dedicated engineers and scientists that can go down, share that back with more scientists back in the UK and around the world. And then you need people to look after those people. So suddenly now we're starting to grow. We need a chef who's going to keep everybody fed. We need a doctor to keep everyone healthy, and a communications officer to make sure we can get all this information back. And now we've got quite a substantial little team. So now you can't expect them to live in a tent for a year at a time. That's not going to work. So now it starts to grow. Now we add generator mechanics to keep the power on. We need plumbers and electricians to keep the station running. And it doesn't stop there, because now you've got a big group of people. And now you want to do loads of science that you're down there. So now why limit it to the base? So we add vehicle mechanics to look after all of our vehicles, field assistants to help get you out in the field and keep everyone safe, and a team leader to basically manage everybody. So there we go. There's a team that goes down to Halley to study all sorts of effects around the floating ice shelf and Antarctica in general. But it doesn't stop there. So that's just the team. That's just the team that goes down. We then need to get them there. So now we've got research vessels and cargo vessels. So this is our old vessel, the Ernest Shackleton. We'd use that to take people and cargo down. So you've got a whole team of mariners on board. ABs, again, chefs, officers. There's just so many people that are involved with the full process. And it doesn't stop there, because now you need actually an air crew. You need an air crew to get out to deep field sites and to deliver people to very interesting places that you'd never get to go to. And it doesn't stop there, because again, you need a whole bunch of people back in the UK to coordinate the full process. So the real strength of it is our administration and logistics. So those are just some of the roles that are involved in working in polar science. So as I said, I'm an engineer, and I'll talk you through my route into polar science. So it will be a bit of an engineering talk. Don't worry, I've tried to sneak in some pretty pictures in between. You have to just get through the technical bits, but I think they're cool by themselves. So my background is I graduated with a BSc in electrical engineering from the University of the Witwatersrand in South Africa. Once once I graduated there, I ended up getting my first job with the South African National Space Agency. And I did a summer season at Sanai, which is the South African Antarctic base on the continent. After that, I actually went for a full year on Marion Island, which is this tiny little island right over there. And basically, that was a 10 to 12 person team. You get dropped off on the island and they say, good luck. So once you're down there, you're all there as a team group. You've got to look after each other. You have meteorological experts. You've got, again, station support staff. You get birders who are out to look at the marine birds. You get marine mammal specialists who are looking at the seals and killer whales. And myself, I went down as a space weather engineer, which is a fancy term for someone to keep the electronics running. So that's when the bug bit. And from there, I ended up doing a MSc and then going straight into working for the British Antarctic Survey. And I'll now show you some of the places I've been involved in and some of the tools that we work with. So this is our previous research vessel, the ROS James Clark Ross, and it was an absolute privilege to work there. We ended up going all over the place, from down to South Georgia, all along the Antarctic continent, deep into the ice fields. It's fantastic. And it really did some world-class science on a vessel that was 30 years plus old. And, you know, for that sort of age, it was very impressive what we were able to achieve. So here is an example of one of our instruments called a CTD. It measures conductivity, temperature, and depth, which we lower through the water column. So you can process a single point spot in the ocean. We've got a whole bunch of other instruments on there, fluorometers, transmissometers, power sensors, LADCPs to measure current velocity. So what you start to do is you can profile a large section of the ocean by doing pinpoint measurements. So that's quite an important tool. And we worked with a specialist team of engineers at BAS. We've actually now got a new one, which is a metal-free titanium CTD on the Sir David Attenborough. So all of the work we've done on here, we've actually taken over onto the SDA. I've actually just got off of there today, and it's a fantastic vessel. I can't wait to show it off to everybody. So if you haven't seen it, please do look at it afterwards. And this is just a typical example of the view from the office. This is some other examples of science that we did off the JCR. So this is a floating iceberg. And from there, we'd get lowered off into the side, collect some of the ice, and then we'd run isotope analysis on there. So again, some very cool stuff. From the ships, we also get involved in going to the stations. So this is a picture of Halley, which is our Halley 6, which is our base on the floating ice shelf. Unfortunately, a number of years ago, it became unsafe to keep people there throughout the year, which started quite an exciting project of automating Halley. So we had to go back to all of our instruments that we had down there that typically had an on-hand engineer to look after it throughout the year. And we had to completely change how we ran that. Everything had to be automated so that we could control it from the UK. But that's no good if you haven't got power. So one of the systems that we worked in was the microturbine generator, which is the center container here. There's a 3D sort of image of it. And basically what it is, it's a jet engine. So a standard generator needs quite a lot, or a standard diesel generator needs quite a lot of maintenance. So we got a nice new jet engine, and that, I think its first maintenance interval was 9 months, and that's to change an air filter. So that's not much of a concern in such a clean area. So by running this, we're able to run and keep the power on the station for a full year without people on hand to keep maintenance. But we can't just run that without knowing how well it's working. So I got involved in installing the full instrumentation package that monitors the environmental parameters around it. You know, what's the fuel level? How much are the pump pressures? What are the pump pressures doing? All the secondary information that can tell you how well things are running, and you can preempt problems before you arrive in the field. So that was quite an exciting project. And by doing so, we've actually been able to keep all of our science running down south, which is, again, quite a big achievement in its own right. Rest of the engineering, we thought we saw some nice pictures. So this is Halley midwinter. And again, it's just one of those things, treats of the job. You get to see things like this, which again, very, very special. Once we leave the stations, you can then also go to some of our island sites. So we do a lot of work on islands as well. So this is a Gen 2, or hang on, no, not a Gen 2. I think it's a macaroni penguins. I might get that wrong. So you have a penguin colony here. So what we have now is marine bird researchers who want to go and study the health of the colony. Because by studying the health of the colony, you can infer the health of the oceans. So one of the questions is sort of asked is, if you were to weigh a penguin when it goes out in the morning and weigh it when it comes back, you know how much it's eaten, you know how good the oceans are. But it's very tricky to try and catch a penguin in the morning, weigh it, and then find the same penguin again later that day. Penguins also don't appreciate getting weighed, and it's also not fun for the scientists. So what we do is we've built something called the penguin weigh bridge. So we put that on the route, so as they're hopping down to the ocean, they hop across the weigh bridge, and we're able to scan them, scan their weight as they go out, and we do the same coming back. And this is, again, a far better way of getting that same information. Poor fingers and the scientists didn't get bitten as much. So, so this is some of the engineering that we get to do. Here's another example. This is also on Bird Island. This is a repeater station for the radios. So it's quite important that as people are working around the island, that they're able to stay in communication. But it is in the middle of the island, so that's a typical commute to work. A little bit better than the M25. And again, just nice, pretty pictures of the penguins. They really are as cute as they look. So yeah, it's worthwhile showing that. This is another example of some of the engineering that we do. So this is a field site. This was done at Beamish. It's a hot water drilling project. So the idea is that you use a massive hot water reservoir and a long pipe, and you slowly melt your way through the ice, which again, there's a whole bunch of very interesting questions we asked that. So one of the things we're aiming to do is to melt our way down to a subglacial lake, which is a sealed pocket of water that's been sealed away from the rest of the world for many, 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 many years. But you still need to be able to do that. You need to do it well. So this is a instrumentation package that we've built to assist us in the engineering of and the process of making that hole. So if we use lots of hot water to make that hole, you end up using a lot of energy. Now, if you don't make that hole big enough, instrumentation gets caught. If you make it too big, you've used far too much energy, which is ultimately fuel, which just makes it a lot more difficult of a process. So we built this instrumentation package to measure the hole parameters, to basically compare against the models, and that way we can drill optimally and as efficiently as we can, which is, again, a special way that we do our field sites. It's quite small, quite focused, but very precision. And just some very interesting pictures of it looking down the borehole. So. And other projects that we're involved in, so this is the Prion UAV project. So this is a 4-meter wingspan UAV, and the idea is we can fit all sorts of instrumentation to this. It can go up and it can fly for about 12 hours or 1,000 kilometers, and it allows us to conduct research over far larger period or far larger areas of ice than we have been in the past, using significantly less fuel. I think to do 12 hours, 1,000 kilometers, we're going to use about 4 liters of fuel. So again, this is the way forward. We're starting to plan ways of going down. I'll be taking this down next year for the winter season. So that should be quite exciting. And here is just a very nice picture of the ship traveling through the Lemaire Channel. So again, I think one of the big things when I went into engineering is there was a big concern of, oh, if I'm an engineer, I'm going to end up working in a factory somewhere. And that's not what I wanted. And I started looking into it, and there are options out of it. There are definite needs for engineers to go into Polish science to assist in getting data back and to find novel solutions to new problems. As we're heading into net zero, obviously we need to find new and better ways of doing the same work. So yes, there's a definite need. So there we go. Short and sweet, very quick. I've left loads of time for questions, so please feel free to ask.
Beg your pardon. That was super interesting, and yes, plenty of time for questions. I'm just going to relay the questions so that our audience online can also hear. So on the previous slide, there was another smaller boat. I think it was it a sailing boat? Actually,
that was a sailing boat that we actually passed in the Lemaire Channel. They were just down there. That was a bit unique. We normally don't see a lot of tourists.
Another question? Sure. Yeah, interesting question. In terms of visiting Antarctica, how does that work in terms of getting permission?
I'll be honest, I've never had to investigate that. So Antarctica does work under so there's a number of nations that all signed on. So that sort of sets how we want to work in Antarctica, sort of the level of environmental responsibility, waste management, what you can and can't do, resource, So basically, there's a number of countries. I think it's about 16, but don't quote me on that too much. So there's a lot of countries that basically signed on and said, we will operate responsibly within this region. UK is one of them. South Africa is another one. There's a number of countries, and everyone sort of follows those rules. I don't know as far as tourism goes. I don't know what you would have to do. I don't know. I don't know. You'd have to call. That is an interesting question.
It is strict, though. I think.
I think it is strict. As I said, I've never have been fortunate enough just to have a ticket delivered. So.
Right. There's a young man here at the front.
How long do you go there for?
Nice. How long do you go there for at a time?
Well, typically it's approximately 3 to 4 months. So when we go away on the ship, we normally join for about 3 months, which normally accommodates about 3 different scientific cruises. So we'll go out with a science party. We'll do a very specialized set of science. We'll come back, we'll drop them off, and we'll start again with the next set, which is quite nice because, again, you get brand new science every time you go out. And then when you go to the field, again, there can be anything from 14 months if you're doing a full winter, to maybe a small field operation, which is, again, typically 3 to 4 months. Yeah.
Right. Another question from one of our younger audience members here.
Are you going to be going on the Sir David Attenborough ship?
Yeah, I'm interested in hearing that as well. Are you going to be going on the RRS Sir David Attenborough ship?
I definitely will, actually. I was lucky enough to sail in on the Thames on Wednesday, which was a very special thing. I've been spending the last couple of days on there. I will be going down on some of the early scientific cruises. So my role is to commission a lot of the scientific instrumentation. So we, as I said, that brand new CTD. I'm very excited about that. My friend, actually, I'm going to point him out, the mechanical engineer back there helped me design the frame. It's a full titanium frame. It's the sort of thing you can't buy from a shop. Everything had to be custom designed, and it's very specialist. So I'll be going down on some of those early cruises, adding more and more instrumentation as we go. So it'll be air sampling systems, rapid cast systems, which measure the temperature profile of the water, XPTs, which do a similar job, CTDs. We'll be doing coring systems. We have a giant piston corer, which is a 40-meter long tube, which will deploy off the side. It's basically just a long pipe with a big weight, and it lowers down to the ocean and sinks into the mud. So you can get a 40-meter length of core. You bring that up, and then you can analyze the sediment layers. So we'll be getting involved in quite a lot of the science in the coming months.
Another question for a gentleman here at the front. Right, nice pertinent question, tough one to answer. With your experience, how serious is the climate issue?
It is very serious. So I'll give you a bit of a sob story in my own little rights. I was lucky enough, I was given the choice of some Arctic cruises. So I went and I had a look at what the Arctic cruises had planned to do, and I had my choice of them. And I'll be honest, I was really hoping to see a polar bear. So I looked at all the specifications for the cruises, and one of them was designed to go along the ice edge. So they'd pre-planned what they expected it from the previous year. And I thought, well, this is great. I'll go on that cruise. We'll sail along the ice edge. When I got there, there was no ice along that route. It had already receded. It's real. It's there. It is problematic. And it's showing year on year. You can actually tangibly see the results. So yeah, it is problematic. It's not doom and gloom. The point is that we can understand these problems now. We can recognize them, and we can all work towards making it better. It's not the end. It just needs people to make that change, the commitment to. That was it. It was a repeat study. So again, they anticipated being it there, and it wasn't there. And again, poor me, I didn't get to see a polar bear.
I think we have another question here from the front. Right. So the Sir David Attenborough research vessel, if you compare it to previous research vessels, what else does it offer?
Oh, it's just unbelievable. To be honest, I can go on about the SDA all day. The lab space facilities are far greater. To be honest, I actually think we were told that the lab space facilities on the SDA are more than we have in our BAS building. So the facilities are far greater. The feature set, so I'll give you a very small example, the moon pool. The moon pool is a brand new feature that we've never had before. So it allows us, one of the big things scientists say is as soon as we get into the ice, just as it's getting interesting, we can't do a science. We can't deploy things into the ocean because there's ice in the way. Now what we can do is we can get to brand new areas and we're still able to deploy the same instrumentation we have. That CTD we'll be able to put down, mud coring. So we're able to get to the sea floor now, where previously we wouldn't have been able to. The ice would have been there. And that's just one of them. We have now dedicated labs for atmospheric measurements, which we haven't had before. We've got a whole new host of meteorological instruments that we can run throughout the year. So as a scientific platform, because that's the real thing, it's a platform for the future. A lot of the space is also very malleable. So the thing is, as we're getting new science and new technologies, we've still got the space to deploy them. So for example, autonomous fleets of one of the instruments called Sailboy. We have the options of actually deploying numerous instruments that can operate autonomously from the ship, which again, we could do in the past, we just didn't have the space to deploy more. So as a platform, it's fantastic. It's giving us a whole new range of features and facilities that will get us into the future. And it's all been future-proofed, which is nice. There's a lot of space which has been left generic enough to accommodate for new uses cases. So yeah, it's very exciting. I'll be honest, the SDA is something I'm really looking forward to sailing on in the future.
And again, if you haven't seen it yet, it is still here until 8 a.m. tomorrow morning. So we've got another question here from a young lady at the front. So prior to deployment into Antarctica and those harsh climates, do you have to undergo any special training?
So on the ship, not as much. Typically, everybody gets a little bit of first aid training, but the ship is actually quite comfortable. I'll be honest, it's almost like working in the office. It just tilts occasionally. So we do have to get some basic mariner training in the sense that we have something called a PST, so it's a personal survival training. It's how to deal with putting life vests on, understanding alarm signals, what to anticipate if you had to eject. But for the ship, not that much. When you go to the field, we do a lot of specialist training. So it's how to cope in very cold conditions, how to basically look after yourself when you're there, because we can't accommodate to have doctors on hand, full field crews. So there's a lot more specialist training for that. So yes, basically you need everybody to be trained up to a certain level for emergency situations, which is quite nice. But on the ship, no, not so much. As long as you're competent in your role, you're good to go.
So the ship itself is very comfy, I gather.
It is very comfy. I won't lie. There's no getting around it. It's a very nice new ship. We do have a lot of very, very comfortable facilities on board. Very nice catering department, so that the food on board is great. Earlier this year, I put on about 6 kilograms. It's just the lack of being able to go out and run in the evenings and just really good food. So yes, we've got that. We've got gym facilities. We have sauna facilities. And a lot of this sounds extravagant, but you've got to understand the context. For a lot of these people, they're living on board for half the year. They're away from friends. They're away from family. It's these little features that actually make it more enjoyable when you're away. It just gives you that little break. You know, when you've missed your mother's birthday, your father's birthday, you've missed that wedding, to be able to sit as a little family group and actually live comfortably on board makes a massive difference to the morale on board and just keeps everybody going. And that's something that's been done very well on the SDA. It's a very comfortable ship. You feel homey when you're there. And again, as I say, small features, but makes a big difference in the long run.
Mm. Another question from a gentleman at the back here. If something goes wrong in Halley 6 in the middle of winter, can they fix it? Or what happens?
Well, this was a part of the concern. So Halley 6 used to have personnel year round. Unfortunately, when they moved it, because being on a floating ice shelf, it drifts, I think, approximately about 1 meter a day out towards the water. So it reached the point where it was getting a little bit of a concern. So it was a big project. We moved it inland. We moved it to a site with lots of research done on it. Unfortunately, right near the end of that project, we found that there was another big crack in the ice heading towards it. Now, rather than risk it, the call was made that we would remove people just to keep everyone safe, because midwinter, you can't get to it. It's dark, the weather conditions don't allow, so it wasn't worth the risk. So as we stand now, it doesn't get manned throughout the year. We have it fully autonomous because of the fact we can't get there. So.
Another question from the young gentleman at the front. Do you mean the Sir David Attenborough? Thank you. How many times have you been on the RRS Sir David Attenborough ship?
Or many, many times. So I've been involved right from the early builder stage. So we were getting on. So as it was building, I was coming in trying to shape the build to make sure it suited the scientific reasons. So right from when it was just pieces of metal, there wasn't any flooring, there was no lights. Right from that stage, we've been going for fairly regular visits to make sure the build would be correct. And now that it's been a bit more complete, we've been getting on a more regular basis. So earlier this year, I think I spent about 2 months on board, and then lots of shorter visits of about a week at a time, slowly scratching away at the commissioning. So getting a couple more sensors installed, getting it commissioned on the network, adding new instrumentation, getting it measured for things that we can't do now because it's disappearing. It's actually heading south on the 16th of November, and it'll be gone until quite late next year. And when it comes back, they're going to want me to get all of my science working. So I need to have it all ready before it gets back. So yes, all in all this year, it's been approximately about 4 months on board.
Right. Another question here. In terms of, is there an age limit, I suppose, in terms of working in the field? And is there an age minimum to working in the field?
I'm not sure about an age minimum. I think as long as you can do your role, so if you have a role to do, I don't think there's an age minimum. Age maximum, I think it's less of an age maximum, more of a how healthy are you? So everybody that goes down has to go through a medical to make sure that your heart's good, that you're physically capable. Same thing on the ship. You need to be able to at least get to a lifeboat. That's probably the minimum level. But especially now, given the recent COVID things, we have had slightly higher medical restrictions, purely because if you do get into trouble down south, it's a lot harder getting you back. So as long as you're fit and healthy, I think generally you can get on and get going.
I think we've got time for 1 or 2 more questions. Who wants to go next? Okay, the young lady at the front here.
So are there any like icebreakers on the ship? Because when it's like moving more towards the land to kind of go to the stations, so is it like, do they have to break through the ice every time, or is there like a specific route?
Yeah. In terms of breaking the ice, is it always necessary to break the ice where the ship needs to go, or is the ice sometimes already broken, so to speak?
To be honest, it changes year on year. So we get brand new ice patterns every year, and it really does depend where we go. So a lot of the time, the SDA will probably not be mid-ice. It might be doing sort of fairly standard ocean science. So around the islands, we're looking for, again, fish health, ocean science. So when we do end up going to the polar regions, it's very much, we get a lot of satellite imagery. We plan our route as well as we can. The ship itself, the actual shape of the ship is quite flat. You'll notice it's not a sharp cutting edge, which again, a lot of people think, well, sure, you want to cut through the ice. What you actually want is a big flat face, a flat nose. And what you do is you ride up on the ice and you crush it rather than cut it. So you're using the weight of the ship to displace the ice rather than to cut through it. Ice is very, very hard. You can almost compare it to rock rather than anything else. So I think the SDA is rated to 1 meter thickness at a certain speed that it can crush through. And there's a bit of an art form to actually navigating through ice. What I've seen in the past is you actually scrape layers of ice off. So if there's a big field and it's a bit too thick, you would scrape slivers off and you'd work your way through an ice shield or an ice field. So yeah, that's the technique involved. It's quite interesting. If you do ride up on ice that's a bit too thick, and you maybe get a bit caught, you can try your engines. If that really doesn't work, you actually shift the weights along the ship and you wiggle your way out, which is quite interesting to see. I've seen it done where people get cranes out and you actually tilt the crane. So yeah, there's lots of techniques. It's a bit of an art form. At the moment, we actually have 2 captains on board the SDA. We have John Harper, which is our ice captain. He's going to go down the season to make sure it gets through the ice well. Hand on some of that experience to our captain, Will Watley. I think he's been doing a number of talks.
Let's do 2 more questions if we can. There's one more here. Compared to 10, 20 years ago, what's the lowest and the highest water temperature that you've measured?
Water temperature?
Yeah, outside temperature as well, so atmospheric temperature. I guess at sea level? Okay, so general temperature comparisons with 20 years ago.
So I'll be honest, from my personal account, I've only been doing it for 6 years. So I actually can't answer that question. I haven't looked at the data myself. I typically just tend to deal with the instrumentation, making sure it's all working well. I haven't gone to that level of detail, I'll be honest. What I can say is quite interesting. Seawater doesn't typically go more than -2. When it goes to -2, it turns to ice. So the coldest that you get is about -2. And you get these weird little thermoclines under the ice, which actually can heat up quite a lot. So you can get to positive degrees under the ice, and then it sort of goes negative again. And this is a large part of actually understanding. It's not just air temperatures, it's also water temperatures. So you have the Thwaites Glacier is a classic example. You have subcurrents that are going underneath the ice shelf that are eroding it from underneath and causing large chunks to come off. And it's trying to understand that from looking at the seafloor properties and the interaction with the underneath the ice to understand how ocean currents are actually causing a lot of issues. So it's not strictly speaking just air temperature. It is really ocean temperatures, and that's why we do a lot of ocean science to understand the modeling around that. We can understand the cause. We can understand what the big impacts are. We can start looking to ways to mitigate that.
Final question. Should we squeeze 2 in? Okay. 2 more questions from our young audience member at the front here. What are the risks involved in being in the field?
Right. Well, there's lots of risks. It very much depends where you go. So I haven't spent too much time in the field. If you catch that man at the back, he can tell you he's done a lot of time in the field. I've done most of my time on the ships. And on the ships, to be honest, we've normally got about 30 crew and anywhere from 8 to about 30 scientists. The SDA can handle up to about 60, so we can have 90 people on board all the time. So there's not a lot of time spent alone, which is quite nice. And we all just look after each other when we're down south. When you're on bases and you are going out, you then are on much smaller parties, and there are risks. So if you're crossing the ice, you could come across crevasses and you could fall into them. It's a very real risk. Working near the ice on the ocean front, you could fall in. There's a lot of risks involved, but we all work together to mitigate those. So again, health and safety is quite important to us. We all look after each other. We do things safely. Everything's done slow and rational. There's not a lot of people that just say, go and do it. Everything has to be planned years in advance, and that's how we tackle it. So there are risks, but we don't tend to do things that are going to be very risky, if that makes sense.
And our final question for this talk. So question about Halley 6 and safety in terms of it not sort of falling through the ice, let's say, in due course.
So in the past, a lot of the bases were fixed. They were built on the ice. You couldn't move them. They drifted out to a point where it became dangerous, or they got crushed by ice and crushed by the snow. Inevitably, you would then have to rebuild a new base, and it would drift out to sea, and it would be lost. However, Halley 6 is actually built on skis. So it might be hard to see, but each of these modules has feet. So you can actually drag them. So you can move module by module. So as it gets out too far, we can actually come back and just move the whole station back to a new site. So it makes it a reusable base, which is quite nice. There's obviously a lot less waste involved, and a lot less cost involved. So that's how we get around that issue. The whole base can actually just be pulled to a new location. Which again it's fantastic to see this massive building. The scale is hard to see from that, but it's huge. And we just come along with a big tractor, pull it to a new site, set up again, and keep going. Halley is quite an important site. Again, as I say, it was known for sort of discovering the hole in the ozone layer. Funny enough, this white container there actually contains what we call the auto Dobson. So the Dobson was the instrument used that was found that. We've now automated that, so we can continue our measurements throughout the year. And that's it. That's the actual platform with the actual device doing the actual data, which is quite nice. And it's all on skis. So once we get to a place where it is risky, we just come back, move it back inland, and we can maintain that data set. So it's quite an important site.
Good. Carson McAfee from the British Antarctic Survey, thank you very much, and thank you.
Thank you, everybody.
Should we begin? So, hello everyone, and welcome to the seminar room at the National Maritime Museum, and welcome also to the final couple of hours of this Ice Worlds Festival, all about polar science and old and new technologies, and of course the very special chance to get a close-up view of the RRS Sir David Attenborough research vessel. Which I'm told leaves at 8 a.m. Tomorrow morning. So do grab that opportunity to take a look at it if you haven't already. But for now, we've got our last talk of the day, our 4 p.m. slot, and this will be about understanding the Thwaites Glacier, popularly dubbed the Doomsday Glacier. So we're ending on a cheerful note. And so this talk will introduce the big questions that concern the fate of the glacier, which is about the size of Britain. What happens if it fully collapses? The International Thwaites Glacier Collaboration has united researchers from across the world to gain an understanding of how this important glacier flows, fractures, and retreats. And with me here, I've got Anna Crawford, who is a researcher based at the University of St. Andrews, and who focuses on understanding the ins and outs of the glacier. So Anna, over to you.
Well, thanks so much. And thanks you all for joining me with the last talk of this great event. Yes, my name is Anna Crawford. I'm a postdoc at the University of St. Andrews, and I am specifically researching the Thwaites Glacier with this collaboration that's called the International Thwaites Glacier Collaboration. And I'm going to get into kind of why we're so interested in Thwaites Glacier itself and what this international collaboration is doing to learn more about it during the talk today. I'll first just really briefly introduce myself and my background. You can tell that I'm not from this side of the pond. I grew up in northern the US, did most of my education, my postgrad work in Canada, and I studied how massive icebergs in the Canadian Arctic deteriorated. So these are actually pictures of my work, oops, jumping ahead here, my work on these massive icebergs. You can see that they're the size of cities. They can be hundreds of square kilometers in size when they break off of the glaciers from where they originate in Greenland. But that was my past days of doing sexy field work, and now I'm behind a screen. So now I am part of the Thwaites Glacier Collaboration, which I'll get into, and that has numerous field aspects of the work. But I'm behind the computer taking the data that my colleagues collect in the field and generating 3D models of glaciers, and then poking and prodding them in different ways to see how they will evolve in the future. So I want to introduce Antarctica a bit, if you haven't gotten enough of Antarctica already as you've been walking around. So Antarctica, is over the South Pole, and it is a sheet of ice that rests on land. And that's what we're seeing in the majority of this white area here. There's sea ice that surrounds the Antarctic continent. The sea ice is floating on top of the ocean. The ice that makes up the Antarctic ice sheet is resting on ground. And I'm going to be honing in today on this region. This is, oh, I keep pressing the wrong button. Let's see. Is that showing up for you? That's okay, I can point. Sorry, should have rehearsed this part. I'm going to point. This is the region of interest of the West Antarctic ice sheet. So this is a region that we're quite concerned about in terms of climate change and what could happen to the Antarctic ice sheet in the future. If the West Antarctic ice sheet is lost, that's about 3.3 meters of global sea level rise. We're not close to that yet, and we'll get into kind of more of the ins and outs of our concern about the West Antarctic ice sheet and its situation going forward. So to dive right into that, we have the West Antarctic ice sheet, and we see that it is thinning. So that's what these colors here are noting. And you can see those red areas are denoting a lot of ice loss and thinning of the glaciers in this region. And there's two glaciers that glaciologists have been focusing on for a number of decades. This Pine Island Glacier, and then its neighbor, Thwaites Glacier. And it's already been introduced that Thwaites Glacier is about the size of Britain. And if we were to lose Thwaites Glacier itself, that's about 65 centimeters of sea level rise. So we're quite concerned about this region. Since it's so massive, has such a potential to contribute to sea level rise and is already kind of in retreat. Skip this slide. So already introduced Thwaites as being the size of Britain. I've introduced how much sea level rise could increase if we lost all of the ice that makes up Thwaites Glacier. It is currently contributing 4% of the current rate of global sea level rise of all the glaciers and inputs to sea level around the globe. This is Thwaites itself, so it's the whole basin that's denoted by the blue outline, denotes the edges of Thwaites, and it's kind of flowing into the ocean that's in front of it here to give you a bit of an orientation. So this is an animation to give you a bit more idea of the flow of this glacier. So glaciers flow, and then they also fail and fracture. So I hope you can kind of see here that the ice is flowing this way. It's also fracturing around here, so that's the icebergs that are detaching. And then you also are seeing a lot of movement in front here, and that's the sea ice that's in front of the glacier. And once in a while it breaks up, and you can see that a lot of movement of the glacier kind of is associated with that sea ice receding from the edges. And I just want to give you this animation to have it in your brain to see how Thwaites is kind of set up. So we have the ice moving from the interior of the continent to the ocean, and then we have ice actually flowing on top of the ocean at the edges here. So these are called ice shelves. They're part of the glacier. They're the part that extends out over the ocean. And I'm going to be referring to these quite a bit, in the talk today. So we have two different ice shelves at Thwaites. We have this one up here. It's called the Eastern Ice Shelf. We don't have anything else too creative to call it. This is fairly stable, or has been at least. And I'll get into some new results that are showing us that we're questioning this now. We also have the floating ice tongue. And it's another ice shelf. We're also calling it ice tongue. But you can see it's extremely fractured. And this is kind of it has retreated quite a bit, and it could be lost, going forward. So we've also been, we've already introduced that, this glacier has been dubbed the Doomsday Glacier. And I think I've already given some hints as to why, it's been given that name. So it's very large. It's the widest glacier on Earth with a width of 120 kilometers. We know that it flows very fast, and we know that that flow is accelerating. So you're bringing more ice from the interior of the Antarctic ice sheet and pushing it into the ocean. We know that it is thinning, and we know that parts of it are retreating inland. So it's big, it's flowing fast, and it's retreating already. I'm going to get into this aspect a bit more on the next slide, but it's situated on a bed that slopes downwards as you go into the interior of the ice sheet. And this is a situation that makes it precarious to faster retreat in the future. And we're thinking about this glacier now because it's already retreating, but we're wondering if other glaciers that are in a similar situation as it could kind of retreat like that in the future. So we're using this as kind of a place to learn about processes that could impact glaciers elsewhere. I was talking about that reverse sloping bed, and I hope I'm able to explain these adequately for you. So this is the Antarctic without the ice. So if we were to remove the ice from this map, or from Antarctica, that's what this map would look like. And so we're really interested in this area here. You can see the dark blue colors there, and that means this region is well below sea level. And it's associated with very thick ice, and that's what those red lines there mean. So if we melt the edges that are in touch with the ocean, we're going to push ice into regions where the ground is deeper, farther below sea level, and there's greater ice, amounts of ice in terms of thickness there as well. And this is the situation that makes the glacier so vulnerable to really rapid retreat. And that's because if you start pushing the glacier down a bed that slopes downwards as you go up glacier, you can start exposing more and more of the ice face to warm ocean water. So that can start contributing to more and more melt and retreat. And then with that, you also have more ice reaching the ocean more quickly. So I should just note that is one process that you might hear about in the news. It's called marine ice sheet instability. There's a second instability that we're worried about for Thwaites Glacier and other glaciers that are situated like it, and that's marine ice cliff instability. And it's something that I'm quite interested in. And you'll start seeing this animation play in a second here. It takes a bit to warm up. So if I was talking about those ice shelves that flow out over the ocean, if we lose those, we'll get to a situation like we see at time 3 here, where we have a vertical calving face. And if we continue to retreat over, again, that reverse sloping bed, we're going to get thicker and thicker calving faces. And at some point, the ice could fail on itself because there's so much strain associated with that tall calving face, and the ice can only hold itself up for so long. So I think we should see it fail here. And if it doesn't work, if it doesn't play in a second, I'll just move on. But I'll describe it while we're looking at it. So here we have the glacier. This is a simulation, obviously, of a very idealized glacier flowing from left to right. And we have the ocean surface noted right here. And I'm hoping that it's going to kind of go on us here. This is the ice cliff that I'm talking about. And this is the calving face that's underneath the water. And we're really worried about this part right here slumping and failing on itself. We'll see if lots of anticipation for this one. And I don't want to click it again because it might, there we go. So we saw that there was a bunch of stress that pushed the glacier basically to fail on itself here. And you can imagine if we now push this calving face into thicker and thicker regions, that process is going to happen more quickly. And that's this positive feedback process that we're worried about in this area. So I think I've probably given you enough cause to worry about Thwaites Glacier at this point. It's big, it's retreating, it could retreat faster. So there's a number of us that are now looking and kind of collectively putting our interest and our work to understand Thwaites Glacier better. And that's the International Thwaites Glacier program. And we had one stand in the exhibit hall. We are made up of 8 different projects. And this is another just idealized version of Thwaites Glacier, where we have, again, the glacier flowing from here to the right. And you see that the different projects are named by these really well thought out acronyms like Time and Ghost, Dominoes and Melt and Tarzan. And we're looking at this glacier from all different angles. So we're looking at it from the sea, where we have a ship in front of the glacier, taking measurements of the sea from the seafloor, mapping the seafloor as well. We have teams that are actually on the ice, doing surveys, traveling around the ice, and also instrumenting the ice so that they can monitor it over the year. And then we also have teams like the one I'm on called Dominoes that sit behind that computer that I was showing on the very first slide, doing the modeling. Again, using all of this amazing data that's coming to us from the field, making my models that much better. And I just want to note that all of our work, is showing it's an example of kind of how a collaboration can be greater than the sum of its parts. So all of our work is going to inform, in the end, policy and what you might have heard about the IPCC reports. That's kind of what we're all pushing towards. So we have these 8 different projects that are feeding different aims, but they're all kind of coming together in the end, working to give all of us as society a better idea of what's happening on the other side of the globe. And again, we're really looking at how much ice is going to be lost, how fast, and of course that accounts for how much sea level rise comes with that. So this is the most ambitious field program in Antarctica to date. We have, as I was mentioning, these 8 different projects working in Antarctica for over 5 years together. And it's funded through the US and the UK, and bringing scientists to this glacier from McMurdo Research Station, which is down in this area, and Rothera, which is up on the Antarctic Peninsula. And we're also bringing scientists there via ship, and we'll be doing more of that over the coming years. Our field operations were quite disrupted by COVID, as you can imagine, but we're getting going again this year. And this is just some of the examples, of the different marine infrastructure that are helping us to collect data in front of Thwaites. You have the Sir David Attenborough will be, ours soon enough. We also collect a vast amount of data from the air. The British Antarctic Survey flew some geophysical surveys a couple of years ago, which were particularly helpful for my work, giving us really great data from the seafloor in front of Thwaites and also the bed of Thwaites. So that really helps me build those 3D models to the best accuracy that I can. And then we have people working in the deep field, as I've mentioned. And I am not one of the people in the field, unfortunately, these days. But you can see that it can be a rather harsh environment. But we're also collecting this really important data. And because we're able to pool resources and personnel from both the US and the UK, it really enhances what we're able to do in the field. And just one more, because there's so many great pictures of doing field work. I had to put in 2 slides on this one. There is, I think it's quite amazing when we are able to get data from beneath the glacier. We have, in places, hundreds to thousands of meters of ice resting on top of the land. So you can imagine it's super difficult to understand what's happening underneath that, what that looks like, what the processes are there. So there can be a huge amount of energy put into sampling data, sampling underneath the ice. And what we do is use hot water to drill through the ice, deploy instruments, and collect samples, from that area. And that's a huge amount of energy and work, but it's really, really special data when we can collect it. And then, so we're talking about kind of, ships and aircraft and on ice work. Then we also have a number of different models. And this is where my work comes in. And I use a number of different models for a number of different reasons. So I'm just going to try to briefly explain them so I don't put you all to sleep about modeling. But I use 2 models, specifically called Elmer Ice and HIDEM. And I use 2 instead of 1 because, as I was describing earlier, ice flows and it fractures. And it's really hard to simulate both of those in a single model. So I use 2 different models that are specialized for each and pair them so I can see how the ice fractures after it flows. And my models, I guess I could have done a different orientation to show you, but they're in 3D. So, I can kind of simulate really detailed processes in 3D. But what I ultimately want to do is learn about these processes in a way that I can actually simplify the process. Think of just like a math equation. I might represent icebergs calving by an equation that can then be plugged into a much larger model. So some people are I'm interested in single glaciers. Other people are interested in all of Antarctica in one model. So I have to give them a really simple equation about how iceberg calving works so that it can be represented, in these large-scale Antarctic models. And an example of a larger model is called ISSM. And right here, it's not showing all of Antarctica, but it's showing its predictions of retreat, kind of where the blue lines kind of end for the area that Thwaites sits in. So I'm kind of nearing the end of the presentation, and with that, I get to show you some kind of highlights and new results from our international collaboration. So I was mentioning, that we have ships kind of operating off the near coast of Thwaites Glacier, and there was also this really impressive aerial campaign that took data above the glacier and above the ice shelves that extend out the ocean. And from that, we get these exciting new maps, and I don't know if they're exciting to you, but they're really exciting to me. So we have the extent of the ice shelves that I was talking about again here, And you can see, or you can maybe get an idea of the really great data and maps that we now have of the seafloor in front of the glacier. And we also have, just to orient you, we have the two ice shelves here. This is a different orientation. And we have really great data now of the bed of the glacier just above, upstream of where it touches the ocean. And this is really important for my modeling work because the detailed shape of the bed directs where the retreat is going to go. So we had these troughs and ridges in the bed, and the retreat really follows those troughs. And then where it hits a ridge, it might pause. So the better we can know where those troughs and ridges are, the better we can predict where it's going to retreat into in the future. I think you should remember, yeah, so if we can remember this ice shelf, and as I was describing earlier on in the presentation, we think that we were considering that to be the more stable of the two ice shelves, but we're learning more about it through the models that I was describing. And so now we have the glacier kind of flowing from the top right to the bottom left. This is the ice shelf and it's over ocean. And I'm just going to show you how my model simulates its breakup. And what we see is a major fracture happening diagonally across of it, and then a major iceberg here. And what we're really worried about is how this will progress and potentially lose the ice shelf. And this is all happening because this part is over ocean, but there's a small amount of the ice that's resting on a high point of the seafloor, and the ice is basically compressing itself. And because it's pretty weak ice, it's able to fail in this manner. So those are, and finally, there's going back to my work on marine ice cliff instability. This, it doesn't look like Thwaites, but it's a very idealized block of ice. And I'm using it to study the process of marine ice cliff instability. And this is the one where the height of the ice cliff actually caused the glacier to collapse on itself. So you're seeing that there's a big slumping here, and then the rest of the glacier will fail buoyantly because it will no longer be in an equilibrium state. So I've kind of given you a crash course on Thwaites Glacier and all these new results that we're getting out of our work with the International Thwaites Glacier Collaboration. And of course, there's further work to be done. A lot of it has to do with understanding now that we have a good understanding of the processes contributing to Thwaites Glacier's current retreat, how does that look in the future? How does Thwaites Glacier evolve as we move forward in the era of climate change? And I just want to highlight that the International Thwaites Glacier Collaboration's field teams are going into the field now. So over the next few months, you might hear about Thwaites Glacier in the news. There's usually some media attention, as the field teams are out there and as they come back. So look out for that. There usually is some press releases when we publish new science. So you might hear about Thwaites Glacier work that way. And I hope that there will be kind of more media and more outreach events such as what's been going on here over the years to come. So thanks so much for listening to all that. There's a lot covered there, and I'll take any questions that you might have.
Thank you, Anna. That was absolutely fascinating. And I'm aware I said a bit facetiously at the onset that we'll end on a cheerful note with a name like Doomsday Glacier, but I actually think we have. So thank you. I'm going to field questions. So raise your hand, and if you can state your question loudly, then I'll speak the question into the microphone. Young lady at the back here.
Obviously, there's a lot to be concerned about. Is there anything to be optimistic about?
Yeah, absolutely.
So the question is, there's a lot to be pessimistic about. Where can we find optimism?
Yeah, I think, to start on the pessimistic side again, but I promise I'll turn it around. We are retreating, and we've changed climate enough that we'll inherit some glacier retreat and sea level rise. But what our actions are, look like now will tell us what kind of retreat we get more in the future of. So if we can curb our emissions, there is a good chance that we don't raise sea level rise by that much. Is that? I'm not saying that so eloquently, but our actions today do influence what's to come. We can still change the course of where we're going. So that's really important. And I didn't go into all the different processes at the glacier, and I was talking about instabilities and how this could accelerate upon itself. The retreat could accelerate. There's a lot of questions. There's lots of uncertainties there. So we're still teasing apart to find out if those instabilities are actually going to initiate or not. And there's different ways that the glacier could actually kind of slow itself down as well. So, but I think we need just to, keep focus on our action. Our actions that we take are influential going forward.
Any more questions? We've got one here from a young lady.
Thank you. That's great. Thanks a lot. What do you think we need to do to get politicians to take account of this? I mean, do you think the media teams of these projects should be funded? Because getting the message over is really crucial.
Great question. Basically, the interfacing between cold hard science and the decision makers.
I think that the more media coverage we can get, absolutely, but also the more public interest in events like this all pushes towards politicians being given that social license to act. So I think that's another way that we can influence things. Is because we can change individually, but we also need more systematic changes. So I see kind of a loop happening where our science and people's interest in it, and concern about the issues drives the politicians to act, and then the politicians hopefully driving us to be, and systems in general to change more quickly.
Who else wants to ask a question? Got one here from a young lady at the front.
Yep.
Are there any elements of the Arctic you haven't been able to look at yet, or things you discovered along the way that if you got more funding to do more, what would you do next?
So if your research had more money, more funding, where would your what would you look at next?
Yeah. I guess can answer that for my personal project best. My project. I said it was a 5-year project overall, but the Dominoes one is actually only 3 years, which is a bit sad. And we're just discovering about these instability processes and what they're going to look like. And I could surely use more time to look into how Thwaites itself, like the if and when those instability processes initiate. So that's kind of one thing on my end that I would like more time for.
Question from a gentleman at the back here. So I guess it's a question about international buy-in, not just UK and US.
And yeah, it's nice that you gave me this opportunity to also highlight some other partners.
Sure.
So we do have interest and investment by teams in Korea as well as Sweden, and likely elsewhere, kind of projects where people are involved from outside the US and the UK. And absolutely, I guess I'm going to go back to that question about influencing politicians. And I'm not sure about interacting with those large, heavily polluting countries or emitting countries specifically, but I think it's getting the other large and powerful governments to influence them. That's how I would. Yeah, that's my opinion. That's less hard science.
Right, another question from a gentleman way at the back here.
Regardless of just the UK's involvement. And I don't think it's the politicians. I think it's more to do with the energy companies themselves and the politicians facilitating them.
Multifaceted question. Did you hear it, Anna?
I did hear it. Thank you.
So I think we know who the big polluters in terms. We know which countries pollute. Effectively, how can we think both commercially and world leaders? How can we get them to understand the gravity and to take action?
I guess in terms of like what we can do as scientists is, get the word out there about the results, and work with our partners. For example, at the British Antarctic Survey, have an excellent communications team that help us reach a wide number of people. And I think that we are making inroads in terms of showcasing the importance of Thwaites Glacier and Antarctica. And I think it's convincing, these large governments, research programs run by, that are funded by the government to increasingly fund this work. I would say we're a relatively small community that study Antarctica for the significance of its retreat onto global society. So I do think that there's more investment needed, by those into these really important programs. So I would say, hopefully we can continue to convince those that this work needs significant funding and further collaborations, because this one will end in a few years.
To what extent will your research feature in COP26?
My research personally kind of works into those sea level rise projections, that are out there, and specifically like the International Governmental Panel on Climate Change projections of sea level rise. So I can only assume that the politicians are well aware of those different curves, on the sea level rise graphs. So that's where my work specifically works in. Lots of others involved with Thwaites Glacier collaboration, as well as Antarctic research and the Southern Ocean, are at COP. There's a pavilion just on the cryosphere, and there's others on the oceans, giving talks on the importance of this work, hoping to get the ear of different people that are involved, in the different negotiations that are ongoing.
Let's grab one or two more questions. We're running out of time, but this is very interesting. So, a gentleman here at the front.
Do those hot water drillings
Yeah.
that you mentioned, do they contribute to ice fractures? And have you modeled that?
The hot water drilling, do they contribute to fractures in the ice?
Yeah, I've never heard of a hot water drill hole contributing to a large scale fracture event. I think the scale of the extent of the ice and its thickness means that a local drill point isn't going to cause a large fracture elsewhere. Yeah.
How hot's the water? Just as hot as possible?
There's someone in the back that might know how hot the water is.
Just below boiling. Thank you. One more question, one final poignant question to close this series of talks. Who wants to take it? Maybe one of our younger audience. Ask a tough one. No? Oh.
Right.
Ah, sorry, beg your pardon. Yeah, lady at the front. It's a great question. How do you validate the models?
Yeah, absolutely. That's a
Thank you.
extremely important part of the whole process. For my personal modeling, I really have validated my models on how glaciers evolve in Greenland. So there's some retreat happening there that I'm able to replicate in my model. And that's my validation. But the large-scale continental scale models that model the retreat of all of Antarctica, they actually go way back in time to show that they can simulate sea level rise over millennia. And that's largely how the validation works on the larger scale.
And with that, Anna Crawford from the University of St. Andrews, thank you very much indeed. And thank you to the audience.
Thank you so much.